What if the universe is not as disconnected as we once believed? Imagine two galaxies, each a sprawling metropolis of stars, planets, and dark matter, separated by millions of light years. Vast gulfs of seemingly empty space stretch between them, space so unimaginably large that we once assumed nothing but silence and darkness could fill the void. But what if, hidden in that void, are vast, invisible highways of magnetic energy stretching across the cosmos, unseen bridges connecting galaxies like invisible threads in a cosmic web? These aren't science fiction constructs or figments of imagination. They are very real, and they are known as extragalactic magnetic bridges. The truth is, they could change the way we think about everything, from the formation of galaxies, to the behavior of cosmic rays, to the very structure of the universe itself. But before we continue, subscribe to the channel and like the video. In today's video, we are going to plunge deep, very deep, into the mysterious and often overlooked phenomenon of extragalactic magnetic bridges. We will unravel the layers of evidence, speculation, theory, and discovery that surround them. We'll explore why these structures defy our previous understanding of magnetism in space, how they were discovered, what scientists believe is creating them, and what their existence could mean for our place in the cosmos. Along the way, you'll encounter some of the most mind-stretching questions in astrophysics today. Are these bridges remnants of ancient galactic collisions? Are they the veins of the cosmic web? Could they be the missing link in our understanding of the universe's magnetic evolution? And perhaps most thrillingly, could they be the highways that future civilizations might one day use to traverse the intergalactic abyss? Let's begin with the truth that we now understand but once doubted: space is not empty. For centuries, we imagined the universe as a vast, vacuumed silence where celestial bodies floated in isolation, unconnected and uncommunicative. But over time, science has peeled back the layers of that assumption. We now know that space is filled with plasma, with gas, with radiation, and, crucially, with magnetic fields. These fields thread through galaxies, wrap around stars, and even stretch between galactic neighbors. But it's the discovery of magnetic structures between galaxies, far beyond the domains of star systems and planetary magnetospheres, that shocked the scientific world and opened a new chapter in cosmology. So, what exactly is an extragalactic magnetic bridge? At its most basic, it is a magnetic field structure that exists in the intergalactic medium, linking two or more galaxies together. Unlike the more familiar magnetic fields found around Earth or the Sun, these extragalactic bridges span distances measured in millions of light years. They are invisible to the naked eye, but we can detect them through their influence on particles and light, particularly via the behavior of polarized radio waves and the motion of high-energy cosmic rays. The first hints of such structures emerged through the study of polarized synchrotron radiation, which is emitted by charged particles spiraling along magnetic field lines. When astronomers pointed radio telescopes at regions between certain interacting galaxies, they noticed something astonishing: a signal. Not just any signal, but a polarized one, indicating the presence of a coherent magnetic field. One of the most famous and compelling cases came from the galaxy pair NGC 4490 and NGC 4485. Between these two galaxies, tugged together by gravitational forces and drawn into a dance of cosmic merging, researchers detected a polarized radio signal that could only be explained by a vast magnetic bridge stretched between them. This wasn't a fluke. Further observations, particularly with highly sensitive radio telescopes like the Very Large Array, VLA, and LOFAR, Low Frequency Array, revealed more of these bridges, particularly between galaxies that had undergone close gravitational interactions. Some of the most stunning examples exist between galaxies and galaxy clusters, where interactions are common and the gravitational environment is fierce. These bridges are often hundreds of thousands or even millions of light years long, and their magnetic fields, while faint, often only a few microgauss, are coherent, structured, and persistent. This begs a critical question: how do such massive magnetic bridges form? To understand that, we need to backtrack and consider the role of magnetism in space itself, a role that for decades was largely dismissed or underestimated. For a long time, astrophysicists treated magnetic fields as secondary effects, mere byproducts of more dominant forces like gravity and radiation pressure. But as observations and simulations became more sophisticated, it became clear that magnetic fields are not just passive players in the cosmos. They influence the movement of gas, they regulate star formation, and they can guide and accelerate cosmic rays. More than that, they can shape entire galaxies. The origin of cosmic magnetic fields is still one of the greatest unsolved mysteries in astrophysics. There are multiple theories, but none are universally accepted. Some scientists believe that primordial magnetic fields, faint, omnipresent fields that emerged during the early universe, perhaps even during inflation, seeded the cosmos with magnetism. Others argue that magnetic fields are generated by astrophysical dynamos, particularly within galaxies, where the rotation of plasma can amplify and sustain magnetic fields over billions of years. But extragalactic magnetic bridges are different. They don't exist within galaxies, they stretch between them, and their structure often appears as a consequence of galactic interactions. This has led many researchers to believe that these bridges are forged during galactic collisions and tidal interactions. When galaxies pass close to each other, their gravity can pull out long streams of gas, tidal tails, that stretch into intergalactic space. If the original galaxies have magnetic fields, and most do, then those magnetic lines can be dragged along with the gas, forming coherent magnetic structures that stretch between the galaxies like luminous bridges of energy. But here's where things get even stranger. Some bridges exist where no visible matter is present. That's right. There are magnetic bridges between galaxies where no significant gas or dust has been detected, at least not yet. This suggests that these bridges may not always depend on material connections. Instead, they could be pure magnetic structures, magnetic relics of past interactions, or even persistent magnetic filaments embedded in the cosmic web itself. The idea that the cosmic web, the vast, interconnected structure of filaments and nodes that define the large-scale architecture of the universe, is threaded with magnetic fields is not new. Simulations have long predicted that the universe's scaffolding should carry weak magnetic fields. But observations of magnetic bridges could be the first direct evidence that such predictions are true. If confirmed, it would mean that magnetism is not just a localized phenomenon within stars and galaxies. It is universal, reaching across the great voids of space like invisible currents. And this has profound implications. If magnetic fields truly stretch between galaxies, then they could influence the motion of matter on a cosmic scale. They could act as conduits for cosmic rays, accelerating high-energy particles across intergalactic distances. They could shape the formation of galaxy clusters, guide the flow of intergalactic gas, and possibly even affect the dynamics of dark matter, which, while it does not interact with electromagnetism directly, is influenced by the gravitational structure that magnetic fields help mold. It also forces us to reconsider the lifespan of magnetic fields in space. On Earth, magnetic fields are constantly shifting. Our planet's own magnetic field reverses roughly every 100,000 to 1 million years. But in space, especially in the quiet intergalactic medium, magnetic fields may persist for billions of years, largely undisturbed. A magnetic bridge formed by a galactic collision in the early universe might still exist today, a ghostly echo of an ancient event. And there's more, much more. Some researchers believe that magnetic bridges could be critical to understanding the origin of magnetism itself. If primordial magnetic fields did exist, then their fingerprints might still be found in the intergalactic medium today. These bridges could act as fossils, preserved clues that hint at the magnetic conditions of the early cosmos. By studying them, we might one day solve one of the greatest riddles in modern astrophysics. Where did the universe's magnetic fields come from? But before we get ahead of ourselves, we need to talk about the tools, both observational and theoretical, that allow us to study these hidden giants of space. Radio astronomy is our primary method. When high-energy electrons spiral around magnetic fields, they emit synchrotron radiation, a form of radio light. The polarization of this radiation tells us about the direction and structure of the magnetic field. Observatories like LOFER, Meerkat, and the upcoming Square Kilometre Array, SK, are revolutionizing our ability to detect faint magnetic signals across the cosmos. With their unprecedented sensitivity, we may soon uncover thousands of extragalactic magnetic bridges, mapping the hidden architecture of the universe's magnetism. But even radio telescopes have their limits. To truly understand these structures, we also need powerful computer simulations, models that combine gravity, fluid dynamics, plasma physics, and magnetism. These simulations are run on some of the most powerful supercomputers in the world, and they help us test hypotheses about how magnetic bridges form, evolve, and decay. They also allow us to explore extreme scenarios: collisions of galaxies, collapses of filaments, explosions of quasars, that would be impossible to reproduce in any lab. And yet, we've barely scratched the surface. Space, once considered a barren void punctuated only by stars and galaxies, has revealed itself to be a far more intricate and dynamic environment. Scientists used to believe that once you ventured beyond the bounds of a galaxy, the universe was largely devoid of structure. But as observational technology has advanced, particularly with the advent of sensitive radio telescopes and X-ray observatories, researchers began detecting something unexpected: faint, extended magnetic fields stretching between galaxies. These weren't anomalies. They were consistent, structured, and enormous. These discoveries ushered in a new understanding. The intergalactic medium is magnetized, and in some places, it is magnetized in a highly organized way that connects galaxy to galaxy. Thus emerged the recognition of extragalactic magnetic bridges. The first significant hints of these bridges came from observations of pairs of interacting galaxies. When two galaxies draw close due to gravitational attraction, they don't merely pass by one another like silent ships in the night. Their magnetic fields interact, distort, and in some cases merge. In this turbulence, long filaments of plasma and magnetism are stretched between them. These filaments, hundreds of thousands of light-years in length, act like cosmic tethers, forming literal magnetic bridges that link two otherwise separate galactic bodies. But even more fascinating is the fact that these bridges may persist long after the galaxies have moved apart or merged completely. One of the most striking examples comes from the well-known galactic pair, NGC 4490 and NGC 4485, often called the cocoon galaxies. Radio observations revealed a magnetic bridge between them stretching over 24,000 light-years. This was not merely a stream of gas. It was a coherent magnetic structure with its own strength and behavior. It suggested that galactic interactions don't just distort structure, they leave behind trails of magnetism that persist over cosmic timescales. These observations raised immediate and challenging questions. How do such magnetic fields form in the first place? Are they remnants of the galaxy's original magnetic signatures, or are they generated anew through interaction? And what mechanism allows them to stretch across such vast distances without dissipating? To understand these phenomena, we must delve into the origin of cosmic magnetism itself. The prevailing theory suggests that magnetic fields in galaxies arise from a dynamo mechanism, a process where the movement of conductive material, such as ionized gas, within the galaxy amplifies and organizes magnetic fields. This mechanism works efficiently within rotating bodies like stars and galaxies, but in the intergalactic medium, where density is sparse and motion is diffused, such a process is far more mysterious. And yet there they are, magnetic bridges floating in deep space, maintaining coherence across unimaginable expanses. So, how do we detect these bridges in the first place? The primary method is through radio astronomy, particularly using techniques like Faraday rotation. This phenomenon occurs when polarized light passes through a magnetized medium, and its polarization angle is twisted. By measuring this twist, scientists can infer the presence and strength of magnetic fields. When astronomers pointed radio telescopes at interacting galaxies, they found unexpected patterns in the background signals, distortions and rotations that indicated the presence of large-scale magnetism between galaxies. Another critical tool in this discovery has been the low-frequency array, LOFAR, a European radio telescope network capable of detecting extremely faint magnetic signals. With LOFAR, scientists discovered filamentary structures of magnetic fields stretching between galaxy clusters, often aligned with filaments of hot gas visible in X-ray wavelengths. These findings confirmed that magnetism is not confined to galaxies. It exists in the vast, tenuous regions that make up the cosmic web. The cosmic web itself, an enormous network of filaments composed of gas, dark matter, and galaxies, is the large-scale structure of the universe. It is shaped by the gravitational pull of dark matter and the expanding nature of space. But now, with the discovery of extragalactic magnetic bridges, we are beginning to suspect that magnetism plays a role in its structure as well. These magnetic filaments seem to trace the very same routes as the cosmic web, suggesting that magnetism is an integral part of the architecture of the universe, not merely a byproduct of galactic motion. One of the most profound implications of this realization is that magnetic fields might influence the movement of matter on cosmic scales. Magnetic fields can guide the flow of plasma, steer the direction of galactic outflows, and even deflect cosmic rays, those high-energy particles that travel across the universe at near light speeds. If these magnetic bridges are common, they could act as vast intergalactic highways for cosmic rays, channeling them from one galaxy to another. This would not only reshape our understanding of how energy moves through the universe, but also how galaxies might influence each other over distances previously thought to be isolating. More intriguingly, some theoretical models propose that these magnetic bridges could be remnants of primordial fields, magnetic lines imprinted on the universe during the inflationary period shortly after the Big Bang. If true, that would mean these bridges are not created by galaxies, but rather inherited by them, making them among the oldest structures in existence. They could be cosmic fossils, preserving the magnetic conditions of the early universe. There's also a tantalizing connection to dark matter. While dark matter remains invisible and elusive, its gravitational pull shapes the motion of galaxies and the formation of the cosmic web. Some researchers suggest that magnetic fields might interact with or trace the distribution of dark matter, offering a rare and indirect glimpse into this hidden component of the cosmos. If extragalactic magnetic bridges outline the paths of dark matter filaments, then studying them might bring us closer to unlocking one of the greatest mysteries in modern physics. In recent years, simulations have played a crucial role in understanding these phenomena. Cosmological models using Magnetohydrodynamics, simulations that combine fluid dynamics with magnetic field equations, have shown that as galaxies move through the intergalactic medium, they can stretch and amplify existing magnetic fields. When galaxies collide, their combined motion can twist and shear these fields, forming bridges much like the ones observed. These simulations not only replicate what we see in the sky but also predict new types of magnetic structures yet to be observed. Yet, even with these models, much remains unknown. How stable are these bridges? How long do they last? Are they common across all types of galaxies, or limited to specific interactions? Do they affect star formation in the regions they touch? Can they act as communication channels for civilizations, if any exist beyond our own? These questions push the boundaries of current science and invite future discoveries. The magnetic bridge observed between NGC 4490 and NGC 4485 was not merely a faint trail of matter. It exhibited a coherent magnetic structure with a degree of organization that challenged long-held assumptions about the behavior of magnetism in space. Rather than dispersing or weakening as expected, the magnetic fields in the bridge remained strong and aligned, suggesting that something was sustaining them across vast distances. This structure wasn't just a leftover feature from the galactic collision, it appeared to be a persistent entity, an intergalactic scaffold made of magnetism and ionized gas. To understand how this is possible, it's crucial to revisit the nature of magnetic fields in the universe. On Earth, magnetic fields are familiar in the form of the compass needle pointing north, or in the magnetic pull of a refrigerator magnet. But in space, magnetic fields are diffuse, sprawling, and often invisible. They are generated by the movement of electrically charged particles, a process known as the dynamo effect. Inside galaxies, these fields can be strong, shaped by the rotation of stars, the activity of black holes, and the explosion of supernovae. But outside galaxies, in the vast emptiness between them, we once assumed these forces would be too weak to matter. We were wrong. The presence of magnetic bridges tells us that magnetism can span intergalactic distances, maintaining coherence and strength across hundreds of thousands of light years. The implications are staggering. It suggests that intergalactic space is not only magnetized but structured. These bridges could act as channels for charged particles, guiding the flow of cosmic rays across the universe. They could also influence how matter accretes onto galaxies, possibly affecting their evolution over billions of years. What powers these bridges? The answer remains elusive, but several theories compete for dominance. One proposes that the motion of galaxies during interactions compresses and stretches magnetic fields, causing them to thread the space between the galaxies like taffy. Another theory suggests that magnetic fields were seeded in the early universe, during the epoch of recombination or even during cosmic inflation, and that galactic interactions merely illuminate and intensify structures that were already there. In this view, extragalactic magnetic bridges are not transient features. They are permanent fixtures in a universe where magnetism plays a central, yet often overlooked, role. The detection of these bridges has only become possible in recent years, thanks to the development of powerful radio observatories like LOFAR, Low Frequency Array, in Europe and the upcoming Square Kilometre Array, SKA, which promises to be the most sensitive radio telescope ever constructed. These instruments are capable of detecting the faint synchrotron radiation emitted by relativistic electrons spiraling along magnetic field lines. By studying this radiation, astronomers can map the structure and strength of magnetic fields that are otherwise invisible. Observations from LOFAR have revealed magnetic filaments that span not just galaxy pairs, but vast regions of the cosmic web, the colossal, large-scale structure of the universe composed of filaments, voids, and clusters. Some of these filaments are hundreds of millions of light-years long and appear to be magnetized throughout. This raises an even more profound possibility, that extragalactic magnetic bridges are not rare or unique, but rather fundamental components of the universe's architecture. They may be the connective tissue of the cosmos, linking galaxies and clusters into a magnetic network that underlies everything. This possibility transforms the question from, "Are magnetic bridges real?" to, "How many are out there, and how do they shape the universe?" Already, astronomers are beginning to piece together an answer. Simulations suggest that magnetism in the cosmic web could play a role in guiding the formation of galaxies themselves. The distribution of matter across the universe is not random. It follows the filaments of the web, clumping into galaxies and clusters at the intersections. If these filaments are magnetized, then magnetism isn't a byproduct of galactic evolution, it's a driving force. To study these structures in greater detail, astronomers are deploying not only radio telescopes but also X-ray and gamma-ray observatories. These higher-energy tools can detect the presence of hot gas and energetic particles in the intergalactic medium, both of which interact with magnetic fields. The combination of data across the electromagnetic spectrum allows for a more complete picture. In some cases, researchers have found that magnetic bridges are associated with flows of hot, ionized gas, suggesting they are not just magnetic in nature, but thermally active. They may be sites of particle acceleration, heating, and even star formation under the right conditions. Perhaps the most tantalizing aspect of magnetic bridges is their potential connection to dark matter and dark energy. These two mysterious components make up more than 95% of the universe, yet we understand them only through their gravitational effects. But what if magnetic fields interact with dark matter in subtle, undetected ways? Some theoretical physicists have proposed that magnetic fields could influence the behavior or distribution of dark matter. If true, then studying extragalactic magnetic bridges might open a window into one of the deepest mysteries in cosmology. The potential links don't end there. There is also speculation that magnetic bridges could play a role in the transmission of ultra-high-energy cosmic rays, particles so energetic that they challenge our understanding of physics. These rays may originate from active galactic nuclei, supernovae, or other violent cosmic events, but their paths are often twisted and deflected by magnetic fields. If extragalactic magnetic bridges are common, they could act like superhighways, directing cosmic rays from distant sources toward Earth. Even more provocative is the idea that these bridges could represent a form of cosmic infrastructure. Some theorists have posited that advanced civilizations, if they exist, might be able to harness these magnetic highways for communication, navigation, or even transport across vast intergalactic distances. While purely speculative, the idea is not without precedent. After all, human civilization has always built around natural routes, rivers, coastlines, and mountain passes. Why wouldn't a cosmic civilization do the same? The idea that magnetic bridges could influence galaxy formation and the distribution of matter across the cosmos represents a paradigm shift in astrophysics. These structures may serve as cosmic scaffolding, guiding how gas, dust, and dark matter collect and form larger celestial structures. Unlike gravity, which pulls objects inward, magnetic fields can direct movement along field lines, shaping the paths of charged particles and influencing the angular momentum of galactic material. This directional guidance can help determine how spiral arms form, how galaxies spin, and how star-forming regions emerge over time. Moreover, these magnetic bridges may offer insight into one of the greatest mysteries in modern cosmology, the cosmic web. The cosmic web is a large-scale structure of the universe, composed of filaments of dark matter, gas, and galaxies that stretch across intergalactic space like the threads of a spider's web. Scientists believe that extragalactic magnetic bridges might be the visible, energetic manifestations of these threads. In other words, these bridges could be the skeleton of the cosmic web. What we're actually seeing might be the magnetic component of the universe's structural framework. What makes this even more compelling is the role that cosmic magnetism might play in the behavior of high-energy particles. Cosmic rays, atomic nuclei traveling at near-light speeds, are thought to be guided and accelerated by magnetic fields. If extragalactic magnetic bridges crisscross the universe, they could serve as intergalactic highways for these particles, explaining how cosmic rays reach us from distant parts of the cosmos. This would solve long-standing puzzles about the origin and trajectory of ultra-high-energy cosmic rays that seem too energetic to have traveled through space without some form of guidance or containment. From an observational standpoint, detecting these magnetic bridges presents significant challenges. The signals they emit are incredibly faint, often hidden within the far more intense emissions from the galaxies themselves. This is especially true when the magnetic fields are located in the vast voids between galaxies, where the ionized gas is sparse. It's a bit like trying to detect the hum of a tuning fork in the midst of a roaring thunderstorm. Only in this case, the storm is the far more obvious radiation from galaxies and quasars. To overcome these challenges, astronomers rely on advanced radio telescopes. Instruments like the Low-Frequency Array, LOFAR, and the upcoming Square Kilometer Array, SKA, have revolutionized our ability to study the universe at lower frequencies, which are ideal for detecting faint magnetic emissions. These telescopes are designed to capture the subtle synchrotron radiation emitted by relativistic electrons spiraling along magnetic field lines. By studying these emissions, scientists can begin to map out the magnetic structures that span galaxies and their connections in intergalactic space. In addition to radio telescopes, multi-wavelength observations are becoming increasingly important. The combination of radio, X-ray, and even gamma-ray data allows astronomers to gain a clearer picture of the physical processes occurring in and around these magnetic bridges. For example, X-ray observatories can detect the hot gas in these bridges, while gamma-ray telescopes provide insight into the most energetic processes taking place. Together, these different wavelengths offer a more complete understanding of the phenomena that might otherwise remain invisible to a single method of observation. Interestingly, it's not just the magnetic fields themselves that are being studied, but the particles that interact with them. Cosmic rays, which are high-energy particles originating from distant sources, can be accelerated by magnetic fields. These cosmic rays often travel vast distances, and when they interact with the magnetic fields in these bridges, they can reveal valuable information about the strength and structure of the magnetic fields themselves. Some researchers believe that the cosmic rays might even be able to trace the paths of these bridges, revealing an intricate web of connectivity between distant galaxies and clusters. Looking forward, the potential for new discoveries is vast. With the next-generation telescopes coming online, our understanding of extragalactic magnetic bridges could expand dramatically. The SKA, for example, will be capable of observing the faintest signals from distant galaxies and intergalactic regions with unprecedented sensitivity and resolution. This could lead to new insights into the nature of these magnetic structures, their role in galactic evolution, and their possible connection to phenomena like dark matter and cosmic acceleration. The possibility that these bridges could be related to dark matter is particularly intriguing. Dark matter, which makes up around 27% of the universe, has remained elusive, detectable only through its gravitational effects on visible matter. Could these magnetic structures be influenced by or even interact with dark matter? Some theories suggest that dark matter might have its own intrinsic magnetic properties, or that it could somehow be guided or constrained by the magnetic fields in these bridges. While this remains speculative, it opens an exciting avenue for future research. Perhaps one of the most profound questions raised by the discovery of these magnetic bridges is what they reveal about the nature of the universe itself. For years, we've thought of space as a vast, empty void between the stars and galaxies, a cold, dark expanse of nothingness. But the reality is far more complex and dynamic. Space is far from empty. It's filled with a magnetic structure that binds galaxies and clusters, a network of invisible threads that connects the very fabric of the universe. These structures, these magnetic bridges, may be far more than just cosmic curiosities. They may be fundamental to the large-scale dynamics of the universe. They could help guide the formation of galaxies, direct the flow of cosmic matter, and even influence the behavior of the mysterious forces like dark matter. And as we continue to study these structures, we might find that our understanding of space, matter, and energy is just beginning to scratch the surface of a far deeper, more interconnected cosmic reality. Looking ahead, the study of extragalactic magnetic bridges promises to open doors to new realms of cosmic exploration. Whether they hold the key to understanding dark matter, the evolution of galaxies, or the nature of the universe itself, these magnetic filaments are pointing us toward an entirely new way of looking at the cosmos. As we delve deeper into understanding these extragalactic magnetic bridges, one of the most exciting possibilities is that they could offer insights into the universe's early conditions. These magnetic structures might be remnants or echoes of the plasma-filled cosmos that existed just after the Big Bang. Back then, the universe was an incredibly hot and dense place, where charged particles roamed freely. This primordial plasma was strongly influenced by electromagnetic forces, and it is thought that magnetic fields were present even in this early epoch. The discovery of magnetic bridges stretching across galaxies and clusters could, in a way, be a cosmic relic from those early times, offering a window into a period of the universe's history that was previously almost entirely inaccessible. Furthermore, the study of extragalactic magnetic bridges might help to refine our understanding of the forces at play in the early universe. As the first structures began to form, first as clouds of gas, then as the first stars, galaxies, and clusters, the role of magnetic fields was likely far more significant than we originally believed. These fields would have influenced how matter coalesced, how galaxies were born, and how large-scale structures like galaxy clusters came into existence. Magnetic bridges could be remnants of the network that helped shape these processes, offering clues to how the universe went from being a homogeneous soup of particles to the intricate, organized structure we observe today. The growing evidence of magnetic bridges also raises new questions about the way the universe will evolve in the future. If these bridges are indeed integral to the cosmic web, one wonders how they might affect the long-term fate of galaxies. For instance, could these magnetic structures help slow down the cosmic expansion by exerting a kind of counterforce to the growing repulsion caused by dark energy? Could they even play a role in the eventual fate of galaxy clusters, influencing how they interact with one another as the universe continues to expand? While much of this is speculative, what is clear is that magnetic fields are much more pervasive in the cosmos than we once thought. These magnetic bridges challenge our understanding of the empty space between galaxies, revealing a complex and interconnected universe where invisible forces, such as magnetism, play an essential role in the evolution of the cosmos. The potential discoveries and breakthroughs that could come from studying these magnetic structures are immense. New observations could reshape how we think about cosmic evolution, the nature of dark matter, and even the very fabric of spacetime itself. As astronomers and astrophysicists continue to study these phenomena, we might find that the universe is far more interconnected and dynamic than we ever imagined. In addition to the implications for cosmology, these findings also have practical applications in other areas of science and technology. For instance, understanding the behavior of magnetic fields on such vast scales could help improve our models of plasma physics, which is crucial for everything from fusion energy research to understanding solar storms. In fact, some of the methods used to study cosmic magnetic fields have direct parallels to the study of plasma behavior in laboratories here on Earth. By gaining a deeper understanding of these cosmic magnetic phenomena, we could develop new technologies or techniques that benefit not only astrophysics but also applied science in fields like energy and materials science. Moreover, the study of extragalactic magnetic bridges could also have broader implications for how we understand the very nature of magnetism itself. While we're familiar with magnetic fields on Earth, from the magnets on our refrigerators to the Earth's own magnetic field, these terrestrial examples are mere shadows of the vast, powerful fields found in space. The study of cosmic magnetism challenges our models of electromagnetism, urging us to think beyond our immediate environment and grasp the larger-scale phenomena that govern the universe. As we look ahead, the potential for new discoveries in the study of extragalactic magnetic bridges is staggering. With the advancement of next-generation telescopes like the Square Kilometre Array, (SKA), and the upcoming James Webb Space Telescope, we're poised to gather unprecedented data on cosmic magnetic fields. These tools will allow us to probe deeper into the heart of galaxies and clusters, giving us a clearer picture of the magnetic structures that bind them together, and tracing the invisible threads that stretch across vast distances of space. It's also possible that, as we learn more about the intricate web of connections between galaxies, we'll uncover entirely new cosmic phenomena. For instance, could these magnetic fields somehow be connected to the mysterious forces behind dark energy or dark matter? Could they even offer a new way to look at the fate of the universe? While these questions remain unanswered, one thing is certain: the study of extragalactic magnetic bridges is poised to unlock new realms of cosmic knowledge, transforming our understanding of the universe at the most fundamental level. The universe, it seems, is far more interconnected and magnetic than we ever imagined. The discovery of these bridges between galaxies not only offers new clues about the structure of the universe, but it may also help us understand the forces that shaped it from the very beginning. The cosmic web, once thought to be a simple metaphor, might just be the true structure of the universe, and magnetic bridges could be its most powerful threads. The exploration of extragalactic magnetic bridges presents a golden opportunity to redefine our understanding of the universe. These structures not only challenge our perceptions of space as an empty void but also deepen our understanding of the fundamental forces that shape galaxies, clusters, and the cosmic web. One of the most striking aspects of these magnetic bridges is how they appear to act as connectors, linking distant galaxies and clusters across vast expanses of space. In many ways, they serve as cosmic highways, carrying energy and matter between otherwise isolated regions. A significant aspect of these magnetic bridges is their potential role in galactic evolution. For years, astronomers have studied galaxies in isolation, focusing primarily on their internal structures, stars, gas clouds, and black holes. However, the discovery of magnetic bridges forces us to consider galaxies as part of a much larger, more interconnected system. These bridges suggest that galaxies do not evolve in isolation but are deeply influenced by their surroundings, connected to other galaxies and clusters by these invisible threads of magnetism. Magnetic bridges may also play an essential role in regulating the interaction between galaxies. These structures could help control the flow of matter and energy between galaxies, preventing them from collapsing under the gravitational pull of one another or from flying apart due to the expansion of the universe. This role might be particularly important in galaxy clusters, where galaxies are packed closely together. Magnetic fields could be acting as a stabilizing force, keeping galaxies from spiraling too far from each other or from merging in chaotic ways. In a sense, the bridges may be part of a larger cosmic network that helps maintain the delicate balance of forces that keep the universe in check. Another fascinating avenue for exploration is the connection between magnetic bridges and the mysterious phenomena of dark matter and dark energy. These two elusive forces dominate much of the universe's mass-energy content but remain largely undetectable through traditional observational methods. Some researchers have speculated that magnetic fields, like those in extragalactic magnetic bridges, could have interactions with dark matter, influencing its distribution or behavior in ways we have yet to fully understand. This could open up an entirely new line of inquiry, leading to breakthroughs in our understanding of these fundamental cosmic mysteries. The ability to detect and measure these magnetic structures is also a key point of advancement in astrophysical research. Radio telescopes, such as LOFR and the upcoming SKA, are at the forefront of this research, offering an unprecedented ability to capture faint radio signals from distant galaxies. These telescopes can detect the synchrotron radiation emitted by electrons spiraling along magnetic field lines, a process that provides a wealth of information about the nature of the magnetic fields themselves. With the next generation of telescopes, it is likely that we will be able to study the smallest and most distant magnetic bridges in the universe, bringing us closer to understanding their true role in the cosmic landscape. In addition to observational advancements, computational models are also becoming more sophisticated. Astrophysicists are now able to simulate the behavior of magnetic fields on the scale of galaxy clusters and large-scale cosmic structures. These models help researchers predict how magnetic fields might evolve over time, how they interact with other forces like gravity and dark matter, and how they influence the movement of galaxies and the formation of stars. By comparing these models with actual observations of extragalactic magnetic bridges, scientists can refine their understanding of the physical processes that govern the universe. In fact, magnetic bridges could be a crucial piece in the puzzle of galaxy formation. Current theories of galaxy formation suggest that galaxies begin as massive clouds of gas that collapse under their own gravity. However, this process is not fully understood. Magnetic fields could play a critical role in this collapse, influencing how gas cools and condenses to form stars. The discovery of magnetic bridges suggests that these fields may extend beyond individual galaxies, creating a larger-scale magnetic infrastructure that guides the formation and evolution of galaxies across the cosmos. While it's easy to get lost in the complexities of these magnetic structures, one of the most compelling aspects of the research is the simplicity of their existence. Magnetic fields are a natural consequence of the laws of electromagnetism. They are not extraordinary phenomena but are instead part of the very fabric of the universe. However, their presence on the scale of galaxy clusters and the vast distances between galaxies adds a layer of complexity and intrigue that has only recently come into focus. The implications of these findings are profound. The study of extragalactic magnetic bridges could potentially reshape our entire understanding of the universe. Rather than viewing galaxies as isolated entities, we are now forced to consider them as part of a larger cosmic network, interconnected by invisible forces that bind them together. These magnetic structures may influence not just the galaxies themselves, but also the cosmic environment in which they exist, affecting everything from the movement of gas clouds to the behavior of dark matter. The study of extragalactic magnetic bridges is a rapidly advancing field that promises to reveal a wealth of information about the structure and evolution of the universe. These magnetic structures are not just fascinating cosmic phenomena, they are essential pieces of the puzzle that could help us understand everything from galaxy formation to the mysterious forces of dark matter and dark energy. As technology continues to improve and new telescopes come online, the mysteries surrounding these magnetic bridges will likely continue to unfold, providing new insights into the interconnectedness of the universe. The cosmic web, once thought to be an abstract concept, may prove to be a real, physical structure that is integral to the fabric of the cosmos itself. The study of these structures is not just a journey into the unknown but an exploration of the fundamental forces that shape everything around us. As our understanding of extragalactic magnetic bridges expands, so too does our ability to make new discoveries about the universe's underlying mechanisms. What makes this subject particularly intriguing is how it challenges many of our conventional ideas about how the universe works. Initially, when we first began studying the cosmos, our understanding of magnetism was largely based on phenomena we observed in our local environment, such as Earth's magnetic field and laboratory experiments. However, the discovery of these vast cosmic magnetic bridges has forced us to rethink how magnetic fields behave on a galactic scale. This new perspective reveals that magnetism in the universe extends far beyond anything we once imagined, reaching across enormous distances and influencing cosmic structures in ways that remain largely unexplored. One of the most astonishing aspects of these magnetic bridges is how they seem to act as cosmic sutures that stitch together distant galaxies and clusters. In essence, they function as connectors that bind galaxies, potentially providing a mechanism for the flow of energy, matter, and even information across the universe. This raises a profound question. Are these magnetic connections essential to the formation and evolution of galaxies and clusters, or are they a more recent phenomenon that simply reflects the current state of the universe? The precise role these bridges play in galactic evolution remains unclear. Still, one compelling theory is that they could influence the movement and interaction of gas, stars, and dark matter between galaxies. These magnetic bridges could be part of a network that facilitates the exchange of matter and energy, allowing for the growth or transformation of galaxies over time. Just as the network of roads and highways facilitates the movement of goods and people on Earth, these magnetic fields could serve as the highways for cosmic matter, enabling galaxies and clusters to interact in ways that are currently beyond our comprehension. Furthermore, it's possible that these magnetic structures may help us understand the elusive nature of dark matter. Dark matter, which makes up about 27% of the universe's mass, cannot be directly observed because it doesn't emit or interact with electromagnetic radiation. Yet, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Some researchers have suggested that the magnetic bridges might offer a clue as to how dark matter behaves. If these magnetic fields interact with dark matter in some way, studying them could lead to breakthroughs that provide a more direct method for detecting dark matter or understanding its role in the universe. Another intriguing question is the potential connection between magnetic bridges and the mysterious force of dark energy. Dark energy, which is responsible for the accelerated expansion of the universe, remains one of the most significant unanswered questions in modern cosmology. Could these vast magnetic fields somehow be linked to dark energy, possibly influencing the rate at which the universe is expanding? Some scientists speculate that magnetic fields, like those found in extragalactic bridges, could have an indirect effect on the expansion of the universe by interacting with other forces, like gravity or dark energy itself. While these ideas are speculative, the very fact that we are asking these questions marks a significant shift in how we think about the cosmos. The discovery of magnetic bridges has opened up entirely new avenues for exploration in astrophysics, offering us the possibility of discovering entirely new forces, phenomena, and interactions that govern the universe at the largest scales. With the right technology and methods, astronomers may soon be able to test these theories and uncover more about the hidden connections between galaxies, dark matter, and dark energy. This is where the power of observational technology comes into play. Advances in radio astronomy, for instance, have revolutionized our ability to detect and study magnetic fields on a cosmic scale. Radio telescopes like LOFAR, Low Frequency Array, and the upcoming Square Kilometer Array, SKA, are capable of detecting the faint signals emitted by synchrotron radiation, which is produced when electrons travel at near light speeds along magnetic field lines. This technology allows scientists to map the magnetic fields in galaxy clusters and trace the invisible threads that connect distant galaxies, enabling us to gain a better understanding of the scale and complexity of extragalactic magnetic bridges. Additionally, future space-based observatories like the James Webb Space Telescope will likely provide even deeper insights into the role of magnetic fields in the universe. Webb's ability to observe the universe in infrared wavelengths will allow scientists to study the most distant galaxies and structures in greater detail than ever before, possibly uncovering magnetic bridges that were previously hidden from our view. With a combination of ground-based and space-based telescopes, the study of extragalactic magnetic fields is poised to enter an exciting new era. One of the key challenges in this field is the vast scale of the structures we're studying. Unlike local cosmic phenomena, such as stars and planets, extragalactic magnetic bridges span distances so vast that they challenge our conventional methods of observation and measurement. A single magnetic bridge can stretch across millions or even billions of light years, making it incredibly difficult to study them in detail. To overcome this challenge, researchers rely on sophisticated computational models that simulate the behavior of magnetic fields over cosmic distances. These models are essential for interpreting the data collected by telescopes and for predicting how magnetic fields might evolve in the future. In these simulations, scientists model the movement of plasma, the electrically charged gas that makes up much of the universe, along magnetic field lines. They also simulate how magnetic fields interact with galaxies, stars, and gas clouds, using these models to explore how the magnetic bridges may influence the structure of galaxy clusters and the flow of matter between galaxies. With each new simulation, researchers refine their understanding of how magnetic fields shape the universe and what role they play in galactic evolution. As exciting as these advances are, it's important to acknowledge that we are still at the beginning of a much larger journey. The discovery of extragalactic magnetic bridges is just one of many groundbreaking developments in modern cosmology. The field of astrophysics continues to evolve rapidly, with each new discovery revealing more about the universe's intricate structure and the forces that govern it. The study of cosmic magnetism is likely to be an ongoing area of research for many years to come, with new revelations and insights that could fundamentally change our understanding of the cosmos. The study of extragalactic magnetic bridges is opening up new frontiers in our understanding of the universe. These magnetic structures challenge our traditional views of cosmic isolation, revealing that galaxies and clusters are far more interconnected than we once thought. The potential implications of this research are vast, from redefining the role of magnetic fields in galaxy formation to uncovering new insights into dark matter and dark energy. With advances in observational technology and computational models, the mysteries of these cosmic bridges will continue to unfold, providing us with deeper insights into the universe's most fundamental processes. As we push the boundaries of what we know, we may find that the universe is more interconnected and dynamic than we ever imagined. As we continue to explore the phenomena of extragalactic magnetic bridges, the complexity and intrigue only deepen. These magnetic connections are not just abstract concepts but tangible, albeit distant, threads that weave through the very fabric of our universe. They connect galaxies, stars, gas clouds, and even dark matter, offering new insights into how the universe's components interact. One of the most tantalizing aspects of these bridges is that they allow us to examine the interconnectedness of cosmic structures in ways that were previously unimaginable. When we look at the larger scale of the universe, it's easy to imagine galaxies as isolated entities, floating in space, each with its own set of gravitational forces. However, extragalactic magnetic bridges challenge this assumption, revealing that the universe's structure is far more interconnected than we initially believed. These magnetic fields serve as a conduit for the exchange of energy, matter, and even information across vast distances. Just as the electrical grid provides a network for the flow of energy on Earth, these cosmic bridges may serve a similar purpose, facilitating the flow of matter and energy between galaxies. This interconnectedness has profound implications for our understanding of how galaxies evolve. Magnetic fields can influence the formation and behavior of galaxies in several ways. For instance, they can act as a stabilizing force, preventing galaxies from breaking apart under the influence of their own gravity. They may also play a crucial role in the movement of gas, dust, and stars within galaxies, affecting how these components interact and evolve over time. Moreover, the magnetic bridges connecting galaxies could be involved in the transfer of material between galaxies, facilitating processes like galaxy mergers and the creation of new stars. One of the most fascinating aspects of these magnetic fields is their potential role in the creation of cosmic structures. As matter is pulled together by gravity, magnetic fields could influence how it clusters, leading to the formation of galaxy clusters, superclusters, and even larger structures like the cosmic web. These large-scale structures are not just random collections of galaxies and gas, but rather intricate networks of matter that are shaped by the forces of gravity, magnetism, and perhaps even dark matter. The role of extragalactic magnetic bridges in shaping these structures is an area of ongoing research, but it's clear that they play a significant part in the way galaxies and other cosmic entities come together. Furthermore, magnetic fields in galaxy clusters may be crucial for understanding the mysterious phenomenon of cosmic rays. These high-energy particles, which are thought to originate from supernovae, active galactic nuclei, and other energetic sources, travel across vast distances and interact with magnetic fields in ways that are still not fully understood. It's possible that extragalactic magnetic bridges provide a pathway for these cosmic rays, influencing their distribution and energy. The study of these interactions could lead to new insights into the origins of cosmic rays and their role in the larger cosmic ecosystem. One of the most compelling aspects of extragalactic magnetic bridges is the potential they offer for studying the relationship between ordinary matter and dark matter. While ordinary matter makes up stars, planets, and everything we can see in the universe, dark matter is an invisible substance that is thought to make up a significant portion of the universe's mass. Dark matter does not emit light or interact with electromagnetic radiation, which makes it difficult to detect directly. However, its presence is inferred through its gravitational effects on visible matter. The connection between magnetic fields and dark matter remains an open question, but there are intriguing possibilities. Some scientists hypothesize that magnetic fields could be influenced by the distribution of dark matter, or that dark matter itself might interact with magnetic fields in some way. While dark matter remains one of the most enigmatic components of the universe, the study of extragalactic magnetic fields offers a potential way to learn more about it. If these magnetic fields are, in fact, connected to dark matter, they could provide a new avenue for detecting and studying this mysterious substance. By mapping the magnetic fields in galaxy clusters and looking for correlations with the distribution of dark matter, scientists may be able to make significant strides in understanding this elusive component of the universe. In addition to providing insights into dark matter, extragalactic magnetic bridges may also offer clues about dark energy. Dark energy is a mysterious force that is thought to be responsible for the accelerated expansion of the universe. Its nature is still not fully understood, but some scientists believe that it could be related to the behavior of electromagnetic fields on cosmic scales. While this is still a speculative idea, the connection between magnetic fields and dark energy is something that could yield fascinating results if proven true. If magnetic fields do influence the expansion of the universe, this could have profound implications for our understanding of the cosmos and the forces that govern it. As technology continues to improve, particularly in the field of radio astronomy, our ability to study extragalactic magnetic fields will continue to grow. With new instruments and methods, scientists will be able to observe these magnetic structures with greater precision and at greater distances. This will allow us to probe the interactions between galaxies, stars, and dark matter with unprecedented detail. Moreover, advancements in computational modeling will help researchers simulate the behavior of magnetic fields on cosmic scales, offering further insights into their role in the formation and evolution of the universe. The study of extragalactic magnetic bridges is still in its early stages, but it is already clear that they represent a significant area of research in modern astrophysics. These magnetic structures are not just abstract phenomena, they are central to our understanding of the universe's most fundamental processes. As we continue to explore these cosmic connections, we will undoubtedly uncover new and exciting discoveries that will reshape our understanding of the universe and its vast, interconnected network of galaxies and cosmic structures. Extragalactic magnetic bridges are a remarkable and complex phenomenon that is reshaping our understanding of the universe. These vast, interconnected magnetic fields play a crucial role in the evolution of galaxies, the movement of cosmic matter, and the behavior of dark matter and dark energy. As technology advances, we will continue to uncover more about these cosmic connections and their role in the larger cosmic ecosystem. The study of these magnetic structures promises to be one of the most exciting areas of research in the coming years, offering us the opportunity to explore the deepest mysteries of the cosmos. As we dive deeper into the mysteries surrounding extragalactic magnetic bridges, the vastness and complexity of these structures continue to astonish astronomers and astrophysicists alike. The connection between galaxies through these magnetic fields offers not only a fresh perspective on cosmic interactions but also opens up new possibilities for understanding fundamental forces in the universe. As research advances, one of the most intriguing aspects that continues to emerge is the impact these magnetic bridges might have on our perception of galactic evolution. Magnetic fields are an essential component of many astronomical phenomena, from the formation of stars to the behavior of supermassive black holes. However, extragalactic magnetic fields represent a whole new level of complexity, where these fields stretch across enormous distances, possibly linking multiple galaxies. This idea challenges traditional views of galactic isolation and suggests that galaxies are much more interconnected than we initially realized. In the vast expanse of space, magnetic bridges could act as cosmic highways, facilitating the movement of not just matter and energy, but also information. This interconnectedness has potential implications for understanding galactic mergers and interactions. Galaxies, long believed to be isolated entities in the universe, are actually connected in ways that go beyond gravitational forces. The presence of magnetic fields linking galaxies provides an entirely new layer to this interaction. Rather than simply crashing into each other under the influence of gravity, galaxies may influence one another through these magnetic structures. This could impact how galaxies evolve, change their shapes, or even trigger new waves of star formation. As two galaxies come closer, their magnetic fields may interact in ways that stimulate new activity, perhaps leading to a flurry of new stars, the triggering of supernovae, or the accretion of matter into a supermassive black hole. The influence of these magnetic fields on star formation is a critical area of research. Star formation is often driven by the collapse of gas clouds under the force of gravity, but magnetic fields can play a significant role in this process by either facilitating or inhibiting the collapse. In galaxy clusters, the presence of extragalactic magnetic bridges could affect the distribution of gas, dust, and other materials within galaxies, potentially impacting where and how new stars are born. The intricate dance between magnetic fields and gas clouds could be a driving force behind star formation, shaping the structure and evolution of galaxies in ways we are only beginning to understand. In addition to their role in galactic evolution, extragalactic magnetic bridges could also offer important insights into the nature of cosmic rays. These high-energy particles, often associated with supernovae and other violent cosmic events, travel vast distances across space, often encountering magnetic fields along the way. Magnetic fields in galaxy clusters or along these bridges may affect the trajectory and energy of these cosmic rays, influencing their propagation across the universe. This is an area of growing interest, as understanding cosmic ray behavior is key to understanding the broader cosmic ecosystem. What is the source of these cosmic rays? How do they travel through space, and how do they interact with the magnetic fields that they encounter? These are questions that could be answered by studying extragalactic magnetic fields and their role in shaping the behavior of these energetic particles. As we continue to examine the potential influence of these magnetic bridges, one of the most significant aspects to consider is their relationship to dark matter. The existence of dark matter is one of the greatest mysteries in astrophysics. It is thought to make up a significant portion of the universe's mass, yet it cannot be detected directly because it does not interact with light or other forms of electromagnetic radiation. However, dark matter's presence can be inferred from its gravitational effects on visible matter. In the context of extragalactic magnetic fields, the question arises, could dark matter be interacting with these magnetic structures? While the evidence for this is still speculative, some scientists believe that dark matter could influence the behavior of magnetic fields, or that magnetic fields might interact with dark matter in some unknown way. Understanding the relationship between dark matter and extragalactic magnetic bridges could lead to groundbreaking discoveries that reveal new aspects of this elusive substance. Dark energy, the mysterious force believed to be driving the accelerated expansion of the universe, is another enigma that could be linked to extragalactic magnetic fields. Dark energy is theorized to be responsible for the accelerated expansion of space, yet its nature remains largely unknown. Some researchers have speculated that dark energy might be related to the behavior of electromagnetic fields, particularly on large scales. Could the interaction of magnetic fields across vast distances somehow influence the rate of cosmic expansion? While this idea is still in its infancy, the study of extragalactic magnetic fields offers an intriguing potential avenue for exploring the relationship between these two cosmic phenomena. Another avenue of investigation involves the role that extragalactic magnetic fields play in the distribution of matter throughout the universe. The large-scale structure of the universe is composed of galaxies, galaxy clusters, and vast voids. These structures are not randomly distributed but instead follow a complex web-like pattern known as the cosmic web. Magnetic fields may be instrumental in shaping the formation and evolution of these structures. They could influence how matter clusters, how galaxies form, and how the universe evolves on the largest scales. The presence of extragalactic magnetic bridges may help explain why matter is distributed in such an intricate, interconnected pattern. This research could ultimately lead to a better understanding of how the universe came to be structured the way it is today. One of the most exciting aspects of the study of extragalactic magnetic fields is the potential for future discoveries. As technology advances, particularly in the fields of radio astronomy and computer modeling, we will be able to study these cosmic phenomena with increasing precision. Radio telescopes, which are particularly well suited to detecting magnetic fields in space, will continue to play a crucial role in advancing our understanding of extragalactic magnetic bridges. By studying the polarized light emitted by distant galaxies, we can map the structure of their magnetic fields and explore how they interact with one another across vast cosmic distances. At the same time, new computational models will allow researchers to simulate the behavior of these magnetic fields on large scales, helping to shed light on their role in galactic evolution, star formation, and other cosmic processes. These models will also enable scientists to test hypotheses about the connections between magnetic fields, dark matter, dark energy, and the large-scale structure of the universe. By combining observations from radio telescopes with sophisticated simulations, researchers will be able to create a more complete picture of how magnetic fields shape the universe. Extragalactic magnetic bridges are an awe-inspiring and complex phenomenon that is transforming our understanding of the universe. These magnetic structures connect galaxies across vast distances, influencing everything from the evolution of galaxies to the behavior of cosmic rays. As we continue to study these bridges, we will gain new insights into the fundamental forces that govern the cosmos, including gravity, magnetism, dark matter, and dark energy. The study of extragalactic magnetic fields holds the promise of answering some of the most profound questions in astrophysics and unlocking new mysteries about the universe. As technology and research continue to advance, we can only imagine the groundbreaking discoveries that await us in the years to come. As we continue to explore the vast and intriguing concept of extragalactic magnetic bridges, one must also consider their broader implications for cosmology and the very nature of the universe itself. These immense, invisible threads of magnetic force are not just fascinating phenomena to study for their own sake, but could also provide critical insights into the foundational workings of the cosmos. The behavior of these bridges might offer new clues about the formation of galaxies, the dynamics of galaxy clusters, and the nature of the dark matter and dark energy that dominate the universe's composition. The notion that magnetic fields can stretch across intergalactic distances is profound in itself, challenging our understanding of the forces at play within the universe. The magnetic bridges that connect galaxies could, in some sense, be seen as a form of cosmic network, where different systems are connected not just by gravitational attraction, but by magnetic influence. This could completely reshape how we think about galaxy clusters, turning what we once considered isolated islands of stars into interconnected, dynamic systems that exchange information, energy, and matter. Magnetic fields themselves are deeply entwined with other cosmic forces. For example, the role of magnetic fields in star formation is well known. Magnetized gas clouds can collapse under the right conditions, fostering the birth of new stars. When considering extragalactic magnetic bridges, the fields linking distant galaxies could potentially influence the star-forming processes within those galaxies. The magnetic fields might interact with the gas clouds and the interstellar medium in ways that regulate or enhance star formation, possibly even altering the shape and structure of galaxies over time. The interaction between magnetic fields and gas in different galaxies could thus play a much more significant role in the evolution of galaxies than previously imagined. In this grand cosmic dance, one cannot ignore the role of black holes, particularly the supermassive ones located at the centers of many galaxies. Black holes are known to exert enormous gravitational forces, but they also influence their surroundings through powerful jets of radiation and particles. Magnetic fields are thought to play a crucial role in the formation of these jets. The interaction between magnetic fields in the vicinity of supermassive black holes and the surrounding matter is thought to be one of the key mechanisms that allow these black holes to expel jets at near light speeds. If these magnetic fields are indeed connected across galaxies via extragalactic magnetic bridges, then these links could potentially impact the behavior of supermassive black holes, possibly even enhancing or limiting the production of these high-energy jets. The connection between extragalactic magnetic fields and cosmic rays is another fascinating aspect. Cosmic rays, high-energy particles that travel through space at nearly the speed of light, are believed to be produced by supernovae, active galactic nuclei, and other violent cosmic events. However, their precise origins and the ways they propagate through space are still a topic of intense study. One theory suggests that cosmic rays might travel along magnetic fields, and the presence of these vast extragalactic magnetic bridges could influence their path. The magnetic fields of galaxies, galaxy clusters, and these bridges might either steer or accelerate cosmic rays, influencing how they travel across the universe. The impact of these bridges on cosmic ray propagation could help answer some long-standing questions about the behavior of these high-energy particles and their distribution across vast cosmic distances. At the same time, the role of extragalactic magnetic fields in the larger-scale structure of the universe cannot be underestimated. The cosmic web, the vast, intricate network of galaxies and galaxy clusters that stretches across the universe, is shaped by a combination of gravitational forces and the distribution of matter. Magnetic fields, particularly those that span large distances between galaxies, could influence this web by providing a sort of spatial glue that holds the galaxies and clusters together, or potentially even guiding the formation of new structures. As our understanding of magnetic fields in space improves, we may begin to uncover how these fields affect the evolution of the cosmic web, ultimately influencing the very formation of the universe's large-scale structure. Despite all the progress in our understanding, the nature of extragalactic magnetic fields still remains an enigma. Observing these fields directly remains a challenge, as magnetic fields are invisible to the naked eye. Unlike visible light, magnetic fields do not emit radiation that can be easily detected. However, scientists have devised clever methods to indirectly study them. One such method involves using the polarization of light. When light from distant galaxies passes through magnetic fields, it becomes polarized, and this polarization can be used to map the structure and strength of the magnetic fields. Radio telescopes are particularly adept at detecting this type of polarization, allowing astronomers to see the magnetic fields and study their interactions across vast distances. Through these innovative techniques, we are slowly beginning to unravel the mysteries of extragalactic magnetic bridges. Theoretical models also play an important role in advancing our understanding of extragalactic magnetic fields. Simulations of cosmic magnetic fields are helping to shed light on how these fields behave and interact with one another over enormous distances. By running simulations that account for the interactions of magnetic fields with galaxies, galaxy clusters, and dark matter, scientists can begin to predict how these fields might evolve over time and how they could influence galactic and cosmic evolution. These models, combined with observational data from telescopes and other instruments, are pushing the boundaries of our knowledge and helping to unlock some of the most fundamental questions in astrophysics. In terms of future research, one of the most exciting possibilities is the potential for the discovery of new phenomena related to extragalactic magnetic fields. As we develop more advanced tools for studying the universe, such as next-generation radio telescopes and gravitational wave detectors, the chance of uncovering entirely new aspects of these magnetic bridges increases. The coming decades could see a revolution in our understanding of how galaxies interact through magnetic fields, and how these interactions influence everything from star formation to cosmic structure. A crucial part of this future research involves understanding how these magnetic fields interact with dark matter and dark energy, two of the most mysterious substances in the universe. Dark matter, which is thought to make up about 85% of the mass of the universe, does not emit or interact with light, making it invisible to traditional detection methods. However, its gravitational effects on visible matter provide indirect evidence of its presence. If magnetic fields can indeed bridge the vast distances between galaxies, could they be linked to dark matter in some way? Some researchers believe that dark matter might interact with magnetic fields in ways that we have yet to understand. This connection could be key to solving one of the most profound mysteries in cosmology and physics. Similarly, dark energy, the force believed to be driving the accelerated expansion of the universe, may also have a relationship with extragalactic magnetic fields. Some theorists speculate that dark energy and magnetic fields could be connected through an unknown interaction. Could the presence of these vast magnetic structures somehow influence the expansion of the universe or even act as a conduit for the effects of dark energy? Again, this is an area where further research and observations could yield groundbreaking results, potentially providing new insights into the nature of both dark matter and dark energy. As we look forward to the next steps in our exploration of extragalactic magnetic bridges, the possibilities for discovery are truly limitless. These magnetic fields are not just another curiosity in the cosmos, they represent a key to unlocking the mysteries of the universe itself. With each new observation, each new discovery, we come closer to understanding the vast, interconnected web of forces that govern the universe, and how these forces shape the very fabric of reality. Whether through advancements in observational technology, theoretical breakthroughs, or the discovery of entirely new phenomena, the study of extragalactic magnetic fields will undoubtedly continue to be a cornerstone of modern astrophysics, and may very well lead to some of the most profound revelations about the cosmos in the years to come. As we venture deeper into the fascinating world of extragalactic magnetic bridges, one must pause to consider their potential impact on our broader understanding of the universe. These magnetic structures, extending across vast expanses of space, are not only crucial for understanding the cosmic forces at play but could also reveal secrets about the early universe. How did such massive, coherent magnetic fields come to exist in the first place? What forces shaped their creation, and how have they evolved over cosmic time? These are questions that touch on the very origins of the universe itself. To truly grasp the implications of extragalactic magnetic bridges, one must take a step back and think about how they fit into the larger framework of cosmology. At the largest scales, the universe is an interconnected web, a vast structure composed of galaxies, galaxy clusters, and superclusters, all bound together by gravity. These structures are not static. They are constantly evolving, with galaxies interacting, merging, and sometimes colliding. In this cosmic drama, extragalactic magnetic bridges could be the unseen forces that help to bind these structures together, providing a kind of invisible framework that transcends individual galaxies and clusters. These magnetic fields could act as a cosmic glue, not in the traditional sense of gravity, but in a more subtle and complex way. For decades, astronomers have been aware that magnetic fields are common within galaxies. These fields are strong enough to influence the behavior of charged particles, shaping the dynamics of stars, gas clouds, and cosmic rays. However, the discovery that these magnetic fields can extend across galaxies and even entire galaxy clusters introduces a whole new level of complexity. It suggests that the forces we see acting on small scales in our own Milky Way galaxy may be part of a much larger, interconnected system that spans vast distances across the universe. This realization has profound implications for our understanding of the nature of cosmic structure and the forces that govern it. One of the more exciting aspects of studying extragalactic magnetic bridges is the potential for new discoveries that could change our understanding of fundamental physics. The vast distances between galaxies, on the order of millions or even billions of light years, make it nearly impossible to study magnetic fields across such scales using traditional observational methods. However, with advances in technology, such as the development of increasingly sensitive radio telescopes and new methods for detecting polarized light, we are now able to observe these distant magnetic fields in unprecedented detail. In the coming decades, it's likely that we will uncover even more about the behavior of these fields. As the sensitivity and resolution of our observational tools improve, we may start to see patterns emerge in the way that magnetic fields extend across intergalactic space. Perhaps we will even uncover new types of magnetic phenomena that are currently beyond our imagination. If these bridges are, in fact, influencing the behavior of galaxies and galaxy clusters, it could lead to a paradigm shift in how we think about cosmic evolution. Instead of seeing galaxies as isolated islands, we may begin to think of them as nodes in a vast, interconnected web of magnetic forces, all linked together in ways that we are only beginning to understand. The role of extragalactic magnetic fields in shaping the universe could also lead to new insights into the behavior of dark matter and dark energy. These two mysterious components make up approximately 95% of the universe's mass energy content, yet we still know very little about them. Dark matter, which interacts with gravity but not with light, has been indirectly observed through its effects on the motion of galaxies and galaxy clusters. Similarly, dark energy is thought to be responsible for the accelerated expansion of the universe, but its precise nature remains unknown. Could extragalactic magnetic fields be connected to these elusive forces in some way? Perhaps magnetic fields have a role in mediating or even controlling the interactions between dark matter, dark energy, and ordinary matter. Investigating these connections could help unlock some of the deepest mysteries of modern cosmology. Moreover, one cannot ignore the potential for these magnetic bridges to influence the very formation of galaxies. Magnetic fields are known to play a critical role in the collapse of gas clouds, a process that is essential for the formation of stars. If extragalactic magnetic fields are as vast and influential as current research suggests, they may have a hand in guiding the formation and evolution of entire galaxies. It's possible that these magnetic fields provide a sort of cosmic scaffolding, directing the flow of gas and dust as it condenses to form stars and galaxies. By studying these fields, we could gain a much deeper understanding of how galaxies come into being, how they evolve, and how they interact with one another over time. The implications of these findings extend far beyond the field of astrophysics. If we can learn to harness the knowledge of extragalactic magnetic bridges, it may open up entirely new avenues of technological innovation. Magnetic fields are already used in a wide variety of applications on Earth. Understanding how these fields behave at cosmic scales could inspire new technologies or even new ways of manipulating energy and matter. It's possible that the study of extragalactic magnetic fields could provide insights into fields like quantum mechanics, electromagnetism, and even the nature of time and space itself. As we look ahead, one of the key challenges in this field will be to refine our methods of observation and measurement. The distant cosmic distances involved make it difficult to study these magnetic fields directly. However, with the advent of more advanced telescopes, such as the Square Kilometre Array, (SK), and other next-generation radio observatories, we are poised to make significant strides in our understanding of extragalactic magnetic fields. These instruments, which are designed to detect radio waves and polarized light from distant sources, will allow us to map the magnetic fields of distant galaxies and galaxy clusters in greater detail than ever before. The information gleaned from these observations will likely be critical in unraveling the mysteries of cosmic magnetic forces. Ultimately, the study of extragalactic magnetic bridges represents one of the final frontiers of astrophysical research. These invisible cosmic structures may hold the key to understanding not just the formation of galaxies, but the very nature of the universe itself. As we continue to explore this topic, we may find that the universe is far more interconnected and magnetic than we ever imagined, with vast, unseen networks of force stretching across intergalactic space. The coming years will undoubtedly reveal more about these cosmic mysteries, and as we unlock the secrets of extragalactic magnetic fields, we may very well uncover some of the deepest truths about the universe and our place within it. The story of extragalactic magnetic bridges is not only about the exploration of invisible forces, but also about the quest to understand the universe on a much larger scale than ever before. The idea that these magnetic bridges can connect entire galaxies and clusters of galaxies is one of the most profound realizations in the history of cosmology. It forces us to rethink the nature of the universe itself. No longer can we view galaxies in isolation. Instead, we must consider them as part of a larger, interconnected web of cosmic forces that stretch across vast distances. This realization could forever alter our perspective on the universe's structure and evolution. But what does this mean for the future of cosmic research? In the past, astronomers and astrophysicists had to focus on individual galaxies, studying them one at a time and trying to piece together their individual stories. With the discovery of extragalactic magnetic bridges, however, scientists are beginning to see that galaxies are not separate, isolated objects, but rather integral parts of a vast, interconnected cosmic network. This shift in perspective is akin to realizing that the universe is not made up of individual islands, but of a series of bridges and links that bind everything together. One of the most exciting possibilities that this new understanding brings is the chance to uncover the mechanisms behind galaxy formation and evolution. Magnetic fields play a crucial role in how gas clouds collapse to form stars, and these fields can also influence the dynamics of galaxy mergers. If extragalactic magnetic fields are as powerful as current observations suggest, they could be influencing the way galaxies grow, merge, and interact with each other over billions of years. These fields could even provide us with a better understanding of how galaxies acquire their shapes and sizes, and why some galaxies are larger or more active than others. For example, in galaxy clusters, the presence of magnetic fields could be helping to regulate the flow of gas between galaxies, influencing star formation and the growth of supermassive black holes. By studying how these magnetic fields behave in different environments, scientists might be able to identify the underlying processes that drive these phenomena. In particular, understanding how magnetic fields influence the cooling and heating of intergalactic gas could give us valuable insights into the cycle of galaxy formation and evolution. It's possible that these magnetic fields play a role in regulating the energy balance of galaxy clusters, helping to maintain the delicate equilibrium that allows galaxies to survive and thrive. In addition, extragalactic magnetic bridges could also have important implications for our understanding of high-energy phenomena in the universe. High-energy cosmic events, such as supernovae and gamma-ray bursts, generate immense amounts of energy and radiation, much of which is carried by magnetic fields. If extragalactic magnetic bridges are indeed responsible for channeling energy between galaxies, they could play a role in directing or amplifying these high-energy phenomena. This could lead to new discoveries about the most powerful forces in the universe and how they interact with the surrounding space. Understanding how these magnetic bridges affect the propagation of cosmic rays and other high-energy particles could be crucial for understanding the origins of some of the most energetic events in the cosmos. The study of these magnetic fields also opens up new possibilities for investigating the relationship between ordinary matter, and dark energy. We know that dark matter makes up most of the mass in the universe, yet it remains invisible to traditional methods of observation. One theory is that dark matter interacts with ordinary matter through the gravitational force, but it doesn't interact with light or other electromagnetic radiation. However, it's possible that magnetic fields could play a more complex role in dark matter dynamics, potentially influencing the way dark matter behaves in galaxy clusters and beyond. If extragalactic magnetic bridges are indeed linked to dark matter, they could provide the key to unraveling some of the mysteries surrounding this elusive substance. Similarly, dark energy, which is believed to be responsible for the accelerated expansion of the universe, could also be influenced by the magnetic fields that stretch across intergalactic space. The exact nature of dark energy remains one of the biggest unanswered questions in cosmology, and the discovery of a connection between magnetic fields and dark energy could lead to groundbreaking insights. It could even provide clues as to why the expansion of the universe is accelerating at an ever-increasing rate. If extragalactic magnetic fields play a role in the behavior of dark energy, understanding these fields could be a crucial step in solving one of the greatest puzzles of modern science. Despite the incredible potential of extragalactic magnetic bridges to revolutionize our understanding of the universe, there is still much that remains unknown. For instance, we don't yet fully understand how these magnetic fields are generated and sustained over such vast distances. Are they the result of ancient cosmic events, or are they continuously generated by processes occurring in the present? How do these fields interact with the surrounding cosmic environment, and how do they change over time? To answer these questions, scientists will need to develop new theoretical models and observational techniques that can probe the mysteries of these distant magnetic structures. One promising avenue of research is the study of cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang and provides us with a snapshot of the early universe. By studying the polarization patterns in the CMB, scientists can gain insights into the magnetic fields that existed in the early universe and how they evolved over time. These observations could help to shed light on the origin and evolution of extragalactic magnetic bridges and their role in shaping the cosmos. As technology continues to advance, the next generation of telescopes and space observatories will be crucial for making new discoveries about extragalactic magnetic fields. Instruments such as the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, are already pushing the boundaries of our observational capabilities, allowing us to detect faint signals from distant cosmic objects. These cutting-edge tools will provide us with the data needed to study magnetic fields in far greater detail, and help us build a more complete picture of the universe's structure and evolution. The road ahead is filled with possibilities, but it is also fraught with challenges. The vast distances involved make it difficult to directly observe these magnetic fields, and current techniques have their limitations. However, as our understanding of astrophysics continues to grow and our tools become more powerful, the mysteries of extragalactic magnetic bridges will likely become clearer. What we do know for sure is that these invisible cosmic structures are shaping the universe in ways we are only beginning to understand. The next few decades of research could be some of the most exciting in the history of cosmology, as we unlock the secrets of these cosmic bridges and explore the vast, interconnected web that underpins the structure of the universe. As we continue to probe the deepest reaches of space, we are bound to discover more about these magnetic phenomena and their role in the cosmos. The knowledge we gain will not only enhance our understanding of the universe, but could also open up entirely new avenues of scientific exploration and technological innovation. The study of extragalactic magnetic bridges is a testament to the power of human curiosity and the relentless drive to explore the unknown. In the coming years, these invisible cosmic forces could reveal some of the most profound truths about the universe and our place in it. The significance of extragalactic magnetic bridges lies not only in their ability to connect distant galaxies but also in their potential to deepen our understanding of the large-scale structure of the universe. As we peer deeper into the vast expanse of space, we are continually faced with the realization that the universe operates on scales far beyond our intuitive comprehension. These magnetic structures are part of a much grander design, where galaxies and galaxy clusters are not simply isolated islands but nodes in a vast, interconnected cosmic web. One fascinating aspect of extragalactic magnetic bridges is the way they challenge the traditional view of space as a mostly empty vacuum. We have long considered space to be largely devoid of matter, with stars, planets, and galaxies scattered across this emptiness. Yet, magnetic fields, invisible to the naked eye, weave throughout this vast void, holding the universe together in ways we're just beginning to grasp. The concept of a magnetic bridge spanning millions or even billions of light years suggests that space itself is far more complex and dynamic than we once thought. The implications of these discoveries are not limited to theoretical cosmology. They could also have profound effects on our practical understanding of the universe. For instance, understanding the behavior of extragalactic magnetic fields could revolutionize how we think about cosmic ray propagation and high-energy phenomena. Cosmic rays, high-energy particles that travel through space, are influenced by magnetic fields, and by studying the way they move through these magnetic bridges, we can gain new insights into the conditions of distant parts of the universe. This could have implications for everything from the study of supernova remnants to the behavior of black holes at the centers of galaxies. Moreover, if we can map and understand the full extent of extragalactic magnetic fields, it could also help us make better predictions about future events in the universe. For example, the interaction of magnetic fields with charged particles could influence the behavior of supernovae and gamma-ray bursts, both of which are among the most energetic events in the cosmos. If magnetic bridges can channel or direct energy in unexpected ways, they could potentially influence the way these cosmic explosions evolve, providing us with new ways to study and even predict these spectacular phenomena. There's also the matter of magnetic field strength. While we have a basic understanding of how magnetic fields behave within our own galaxy, the sheer scale of extragalactic magnetic fields raises new questions. How are these fields generated, and how do they sustain their strength over billions of light years? One possibility is that these magnetic fields are anchored in supermassive black holes at the centers of galaxies. These black holes are known to produce powerful jets of energy, which could help explain the existence of magnetic bridges between galaxies. The study of magnetic fields could thus also lead us to a deeper understanding of black holes, one of the most mysterious and extreme phenomena in the universe. In this context, magnetic fields may even play a role in the behavior of dark matter. Dark matter, which makes up roughly 85% of the universe's mass, interacts with gravity but not with light, making it nearly impossible to detect directly. However, if dark matter is affected by magnetic fields, as some theories suggest, then magnetic bridges could provide an indirect way to study it. Understanding the role of magnetic fields in dark matter's behavior might finally offer some insight into this enigmatic substance, which has thus far eluded detection despite its clear influence on the universe's structure. Even more intriguing are the possible connections between extragalactic magnetic fields and dark energy, the mysterious force that is accelerating the expansion of the universe. While dark energy is typically thought to be a property of space itself, magnetic fields may have an unexpected connection to it. If these fields are indeed widespread across the universe, they might interact with dark energy in ways that could help us understand the true nature of this force. Some theories suggest that magnetic fields could amplify the effects of dark energy, potentially contributing to the acceleration of the universe's expansion. If this connection is confirmed, it could open up a whole new field of research that connects the study of magnetic fields with some of the most profound mysteries in cosmology. Looking further into the future, the role of extragalactic magnetic fields may be crucial in the study of cosmic evolution. The interplay between gravity, magnetism, dark matter, and dark energy could determine the fate of the universe itself. Will it continue expanding forever, eventually reaching a state where galaxies and clusters are so far apart that they can no longer interact with one another? Or will some force, perhaps one tied to magnetic bridges, eventually halt this expansion and reverse it, bringing the universe toward a dramatic collapse? These questions remain unanswered, but the study of extragalactic magnetic fields might help us to solve them. At present, the research on extragalactic magnetic bridges is still in its early stages, and much remains to be discovered. Many of the concepts we've discussed here are still theoretical, and observations continue to be refined. However, as our observational capabilities improve, we will likely begin to see clearer evidence of these magnetic structures and their influence on cosmic evolution. The upcoming generation of telescopes, including the Square Kilometre Array and the James Webb Space Telescope, promises to offer unprecedented insights into the magnetic fields that permeate intergalactic space. These instruments will allow us to detect magnetic signals from even the most distant galaxies, giving us a clearer picture of how these forces shape the large-scale structure of the universe. One of the challenges in studying these magnetic fields is the vast distances involved. A magnetic bridge between two galaxies can span millions of light years, making it extremely difficult to observe directly. The signals that scientists detect, such as polarized light from distant galaxies or the distribution of cosmic rays, provide indirect evidence of the presence of these fields. But as technology advances, it may become possible to observe these magnetic bridges more directly, using new methods to map the structure of the cosmic magnetic field. For example, by analyzing the rotation of polarized light passing through intergalactic space, scientists could reconstruct the magnetic field lines that thread through the universe, offering a detailed map of these invisible cosmic structures. In the coming decades, the study of extragalactic magnetic bridges may also offer new insights into the nature of spacetime itself. Magnetic fields are known to interact with the fabric of spacetime, and understanding how they behave on the largest scales could reveal new aspects of the universe's structure. Are these fields part of the underlying framework that governs all cosmic phenomena, or are they merely a secondary consequence of other, more fundamental forces? This is a question that will require years of research and observation to answer, but the study of magnetic fields is sure to provide critical clues. The pursuit of knowledge in this area will undoubtedly inspire the next generation of astronomers and physicists. As we continue to uncover the mysteries of the universe, each new discovery, each new piece of the cosmic puzzle, brings us closer to understanding the true nature of the universe. From magnetic fields to dark energy, from galaxy formation to the fate of the universe itself, the study of extragalactic magnetic bridges is just one of many frontiers in cosmology that is waiting to be explored. The implications of these discoveries will shape our understanding of the universe for generations to come, and it is an exciting time to be a part of this journey. As we continue to peel back the layers of the universe's mysteries, the role of extragalactic magnetic fields and their connections to cosmic phenomena will likely become increasingly evident. Their impact is not limited to simply bridging galaxies across vast stretches of space. These magnetic fields might also act as agents of cosmic evolution, contributing to the development of galaxies and clusters, as well as shaping the very fabric of the universe itself. What's particularly fascinating is the ongoing work to refine our understanding of how these magnetic fields behave and influence cosmic processes. Observations of distant galaxies show magnetic patterns that don't conform to the uniformity we might expect. In some cases, magnetic structures seem to follow the contours of galaxy clusters, suggesting that they might play a role in the formation and evolution of galaxies themselves. In this way, extragalactic magnetic fields might act as both a blueprint and a catalyst for the development of the large-scale structures we see today. The intricate relationship between magnetic fields and galaxy formation is a subject that continues to puzzle astrophysicists. Early models suggested that magnetic fields might simply be a byproduct of the violent processes occurring in galaxies, such as supernovae or the accretion of material onto supermassive black holes. However, as research advances, it's becoming clear that magnetic fields might be far more influential than previously thought. They may not only influence the way galaxies evolve over time but also the way they interact with one another. This interaction between galaxies and their magnetic fields can have far-reaching consequences. For example, in galaxy clusters, the magnetic fields can help regulate the flow of gas and matter between galaxies. This could affect the rate at which new stars are born or even influence the formation of supermassive black holes at the centers of galaxies. Understanding these magnetic interactions could give us crucial insights into how galaxies grow and evolve, potentially unlocking the secrets of galaxy formation itself. The role of extragalactic magnetic fields in the context of galaxy clusters is another area of active research. Galaxy clusters are some of the largest structures in the universe, consisting of hundreds or even thousands of galaxies bound together by gravity. These clusters are often surrounded by a vast halo of hot, ionized gas, known as the intracluster medium, ICM. The magnetic fields within the ICM play a critical role in shaping the behavior of this gas. They can affect the movement of charged particles, the generation of cosmic rays, and even the transfer of energy within the cluster. In some clusters, scientists have observed magnetic filaments and structures that seem to connect galaxies across great distances. These cosmic threads may be a direct consequence of the magnetic fields pervading the cluster. These structures might also help explain some of the unusual phenomena observed in galaxy clusters, such as the formation of large-scale shock waves, which are thought to be driven by the interaction of magnetic fields with the gas in the ICM. One particularly intriguing aspect of this magnetic influence is the possible connection between extragalactic magnetic fields and cosmic ray acceleration. Cosmic rays, which are high-energy particles that travel through space, are thought to be accelerated by various processes, including the shock waves that occur in galaxy clusters. If magnetic fields play a significant role in shaping these shock waves, they could also influence the way cosmic rays are accelerated and dispersed throughout the universe. This would not only help us understand the behavior of cosmic rays but also provide insights into the processes driving high-energy phenomena in the universe. As we look further into the distant past, the study of extragalactic magnetic fields may also help us uncover the secrets of the early universe. The cosmic microwave background (CMB), which is the afterglow of the Big Bang, contains crucial information about the state of the universe in its infancy. Recent studies have suggested that magnetic fields may have been present in the early universe, potentially influencing the formation of large-scale structures like galaxies and clusters. By studying the CMB and comparing it with the magnetic fields we observe today, scientists hope to gain a better understanding of how these fields evolved and shaped the universe over time. In addition to these theoretical advances, new observational techniques are allowing us to probe extragalactic magnetic fields with greater precision. One of the most promising methods involves the use of polarized light, which can reveal the structure and orientation of magnetic fields in distant galaxies. By analyzing how light from distant objects is polarized as it passes through intergalactic space, astronomers can map the magnetic fields that stretch across these vast distances. This technique has already provided valuable insights into the nature of magnetic fields in galaxy clusters, and as technology improves, it will allow us to probe even more distant regions of space. Another groundbreaking tool for studying these fields is the upcoming launch of next-generation radio telescopes, such as the Square Kilometre Array (SKA). These instruments will be capable of observing faint radio signals from galaxies and clusters across the universe, providing us with an unprecedented view of the magnetic fields that pervade these regions. The SKA, in particular, will enable us to study magnetic fields at much higher resolutions than ever before, allowing us to examine the intricate details of how these fields interact with their environment. This could lead to groundbreaking discoveries about the role of magnetic fields in shaping the evolution of galaxies, clusters, and even the large-scale structure of the universe. As our understanding of extragalactic magnetic fields continues to grow, we are beginning to realize just how interconnected these forces are with the broader workings of the cosmos. From their potential role in galaxy formation to their influence on cosmic rays and dark matter, magnetic fields are proving to be a crucial piece of the cosmic puzzle. The study of extragalactic magnetic bridges, in particular, offers a unique window into the nature of these fields and their impact on the universe. With each new discovery, we inch closer to unlocking the mysteries of the universe's most elusive forces. It's clear that these cosmic phenomena represent one of the most exciting frontiers in modern astrophysics. They are not only reshaping our understanding of the universe but also providing us with the tools to delve deeper into the fundamental forces that govern the cosmos. Whether it's through the study of cosmic rays, galaxy evolution, or the origins of magnetic fields, the discoveries made in this field will have far-reaching implications for our understanding of the universe's past, present, and future. In the coming years, we can expect even more revelations as new technologies and observational methods allow us to peer deeper into the universe than ever before. The magnetic bridges that span galaxies and clusters, hidden in the vast emptiness of space, will undoubtedly continue to captivate the imaginations of scientists and enthusiasts alike. What they reveal about the nature of the cosmos, and the forces that bind it together, could very well change the way we view the universe forever. As we continue to venture deeper into the cosmos, the significance of extragalactic magnetic fields becomes clearer. These enigmatic phenomena are far from simple, and their complexity only deepens as we gather more data and refine our observational tools. The study of magnetic bridges between galaxies not only illuminates the forces shaping the universe but also helps us unravel the fundamental physics behind the structures we observe. These magnetic connections might be key to understanding the evolution of large-scale cosmic structures, and the more we learn, the more we realize how little we actually know. One of the most intriguing aspects of extragalactic magnetic fields is their potential link to dark matter and dark energy, two of the most profound mysteries in modern cosmology. While magnetic fields themselves cannot explain the existence of dark matter, their influence on the surrounding space could reveal clues about how dark matter interacts with regular matter. If magnetic fields play a role in the distribution and behavior of dark matter, we might be able to observe this through their effects on galaxies and galaxy clusters. This would be an incredible breakthrough, as dark matter remains largely invisible and detectable only through its gravitational influence on visible matter. Furthermore, the interaction between magnetic fields and dark energy could also offer crucial insights into the accelerating expansion of the universe. Dark energy, which is believed to be responsible for the universe's rapid expansion, remains one of the greatest enigmas in cosmology. Some researchers speculate that magnetic fields, by affecting the way energy and matter interact in galaxy clusters and other cosmic structures, could help explain the nature of dark energy. The study of extragalactic magnetic bridges may, in the future, provide new avenues for exploring how these two invisible forces work together to shape the cosmos. As we explore the interplay between magnetic fields, dark matter, and dark energy, we also need to consider the role of cosmic simulations in advancing our understanding. Computer simulations are becoming increasingly sophisticated, allowing scientists to model complex phenomena like magnetic fields in galaxy clusters and large-scale cosmic structures. These simulations help researchers test their theories and refine their models, offering a deeper understanding of how magnetic fields might influence the behavior of matter in the universe. By comparing simulated data with actual observations, scientists can improve their models and, hopefully, make more accurate predictions about the behavior of extragalactic magnetic fields. The next generation of observational instruments will also play a pivotal role in expanding our understanding of these magnetic bridges. While current telescopes like the Hubble Space Telescope have provided incredible images of distant galaxies and galaxy clusters, the next wave of space-based observatories promises even greater advancements. Instruments like the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, will allow scientists to observe the universe in new ways, enabling us to detect magnetic fields with unprecedented precision. The JWST, for example, will offer detailed infrared observations of galaxies and their magnetic environments, while the SKA's radio capabilities will enable the study of faint magnetic signals from distant cosmic objects. With these next-generation tools, we can expect to uncover even more about the role of magnetic fields in the evolution of galaxies and large-scale cosmic structures. Beyond these technological advancements, there's also a growing recognition of the need for interdisciplinary approaches to studying extragalactic magnetic fields. Theoretical physicists, observational astronomers, and computational modelers are all working together to tackle the many questions that arise from the study of these cosmic bridges. By combining different perspectives and expertise, researchers are beginning to build a more comprehensive picture of how magnetic fields behave on the largest scales. This collaborative effort is essential to making progress in a field as complex and vast as astrophysics, where the smallest discoveries can have far-reaching implications. One of the ongoing challenges in this field is the difficulty in detecting and measuring magnetic fields in distant galaxies. Magnetic fields are inherently weak, and their effects can be hard to isolate from the many other forces at play in cosmic environments. Despite this, researchers have developed a variety of techniques to detect and study magnetic fields, including the use of polarized light and synchrotron radiation. These methods have already yielded important results, but much remains to be discovered. As observational technology improves and new techniques are developed, it's likely that we will be able to detect magnetic fields in even the most remote regions of the universe. Another challenge is understanding the origins of these extragalactic magnetic fields. How did these fields form, and why are they so prevalent across the cosmos? Theories abound, ranging from the idea that they were created in the early universe, possibly as a result of primordial processes during the Big Bang, to the possibility that they arise from the interactions between galaxies and the matter in their surroundings. Whatever the true origins of these magnetic fields may be, their presence in nearly every part of the universe suggests that they play a fundamental role in shaping the cosmos. Furthermore, the behavior of magnetic fields in extreme environments, such as in galaxy mergers and the vicinity of supermassive black holes, is a critical area of study. In these high-energy regions, magnetic fields can become incredibly intense and chaotic, affecting the movement of matter and the dynamics of the surrounding space. The interaction between magnetic fields and high-energy phenomena like supernovae, active galactic nuclei, and gamma-ray bursts is still not fully understood, but it is clear that these fields play a crucial role in the evolution of these dramatic events. Understanding how magnetic fields influence the behavior of matter in these extreme environments could unlock new insights into the mechanisms driving some of the universe's most energetic phenomena. The study of extragalactic magnetic bridges also ties into broader questions about the structure of the universe itself. The distribution of matter, the formation of galaxies, and the large-scale structure of the universe are all deeply connected to the behavior of magnetic fields. By studying how magnetic fields affect the way galaxies and clusters are arranged in space, scientists can gain a better understanding of the forces that shape the universe on the largest scales. The realization that magnetic fields may be a fundamental force shaping the large-scale structure of the cosmos is a relatively new development in astrophysics, and it could lead to groundbreaking discoveries in the years to come. Moreover, magnetic bridges offer a new perspective on the way we view space itself. These fields stretch across enormous distances, defying the traditional boundaries of galaxies and clusters, and suggesting a more interconnected universe than we might have imagined. In this sense, magnetic bridges could be seen as an example of how everything in the universe is ultimately connected, a realization that challenges our previous conceptions of space as a vast, empty void. As we continue to study these magnetic structures, we may begin to perceive the cosmos in a fundamentally different way, one that emphasizes interconnectedness and the complex web of forces that bind all cosmic matter together. The study of extragalactic magnetic bridges represents one of the most exciting and rapidly evolving areas of astrophysics. As we continue to unravel the mysteries of these magnetic structures, we will gain deeper insights into the very forces that govern the universe. From their role in galaxy evolution to their potential connections with dark matter and dark energy, magnetic fields are proving to be far more important than we ever imagined. The future of this field looks incredibly promising, and the discoveries that lie ahead could forever change the way we understand the universe. As we progress in unraveling the mysteries of extragalactic magnetic bridges, it's essential to examine the broader implications these structures might have on our understanding of the universe's evolution. We've already touched upon their potential connection to dark matter and dark energy, but there are even more profound questions about the nature of cosmic structures and the role these magnetic fields play in them. Magnetic bridges are not just isolated phenomena, they are integral to understanding the larger cosmic tapestry, influencing everything from the formation of galaxies to the movement of galaxies themselves. One of the key areas where magnetic fields play a crucial role is in the behavior of galaxy clusters. These clusters, which contain hundreds or even thousands of galaxies bound together by gravity, often exhibit complex magnetic structures. The magnetic fields present in these regions are not just passive bystanders, they actively shape the dynamics of the galaxies within the cluster. In particular, the presence of magnetic bridges between galaxies may affect the way galaxies move through the cluster and interact with each other. The motion of galaxies within a cluster is influenced by both gravitational forces and the magnetic fields present, which can act as a sort of cosmic glue, holding the cluster together while also playing a part in its evolution. In fact, some researchers have suggested that magnetic fields may be responsible for the formation and maintenance of large-scale cosmic structures, such as galaxy clusters and filaments in the cosmic web. The cosmic web is the vast, interconnected network of galaxies and clusters that stretches across the universe, and it is shaped by both gravity and the influence of magnetic fields. Magnetic bridges may help anchor these massive structures, providing a stabilizing force that allows them to maintain their integrity over time. Without these magnetic fields, the cosmic web might be far more chaotic and disordered, with galaxies drifting apart rather than clustering together in these vast networks. The interaction between magnetic fields and galactic motion is especially apparent during galaxy mergers. When two galaxies collide, the resulting chaos creates intense magnetic environments that can dramatically alter the galaxy's behavior. Magnetic fields can become tangled and amplified during these collisions, influencing the movement of gas, stars, and other matter within the galaxies. This may even affect the formation of new stars, as the magnetic fields interact with the gas and dust in the interstellar medium. In some cases, the magnetic fields might even help channel the energy released during the merger, guiding the flow of matter and shaping the outcome of the collision. Another fascinating aspect of extragalactic magnetic bridges is their potential role in high-energy cosmic phenomena, such as active galactic nuclei, AGN, and relativistic jets. AGNs are supermassive black holes at the centers of galaxies that emit vast amounts of energy, often in the form of powerful jets of particles traveling at near light speeds. These jets are believed to be closely tied to the magnetic fields present in the galaxy, with the black hole's rotation and the surrounding magnetic environment working together to launch these jets. In some cases, magnetic fields in the surrounding galaxy or galaxy cluster may form bridges that connect different parts of the AGN, channeling energy and matter in ways that we are only beginning to understand. The role of magnetic fields in AGNs and relativistic jets is a subject of ongoing research. Some studies suggest that magnetic fields can act as a conduit for the energy produced by the supermassive black hole, helping to accelerate particles to high velocities. These fields may also be responsible for the twisting and coiling of the jets, creating complex patterns that are observed in some of the most powerful cosmic phenomena. Understanding how magnetic fields influence the behavior of AGNs and their associated jets could have profound implications for our understanding of black hole physics and the nature of high-energy astrophysical processes. As we delve further into the study of extragalactic magnetic fields, we also need to consider the broader implications for cosmology and the study of the universe's evolution. Magnetic fields are believed to have existed since the early universe, and their presence may have played a significant role in the formation of large-scale cosmic structures. During the first few moments after the Big Bang, the universe was filled with a dense, hot plasma, and magnetic fields could have been generated as a result of primordial processes such as turbulence and the motion of charged particles. These early magnetic fields may have provided the initial conditions for the formation of galaxies and galaxy clusters, helping to shape the universe as we see it today. The study of extragalactic magnetic fields also offers a unique window into the processes that govern galaxy formation and evolution. While much of the focus in cosmology has been on the role of gravity in shaping the universe, magnetic fields are emerging as a crucial factor in this process. By studying how magnetic fields affect the behavior of gas, stars, and dark matter, we can gain a better understanding of the forces that drive galaxy formation and evolution. This could also help us learn more about the conditions necessary for the formation of habitable environments in distant galaxies. After all, magnetic fields are essential in shielding planets from harmful cosmic radiation, and understanding their role in galactic evolution could provide new insights into the potential for life elsewhere in the universe. In addition to their role in galaxy formation and evolution, extragalactic magnetic fields may also help us understand the larger-scale processes that govern the universe's expansion. The universe is currently expanding at an accelerating rate, and while dark energy is believed to be the driving force behind this expansion, the role of magnetic fields in this process remains an open question. Some theorists suggest that magnetic fields could be involved in the acceleration of the universe, either by interacting with dark energy or by influencing the distribution of matter on cosmic scales. If magnetic fields do play a role in the expansion of the universe, this could offer a new perspective on the nature of dark energy and its effects on the cosmos. As our understanding of extragalactic magnetic fields continues to evolve, it's clear that these structures are far more important than we once thought. From their influence on galaxy clusters to their potential connection to dark energy and dark matter, magnetic fields are proving to be essential in shaping the universe. The next generation of telescopes and observational techniques will undoubtedly reveal even more about these fascinating phenomena, and the discoveries we make in the coming years could revolutionize our understanding of the cosmos. The study of extragalactic magnetic bridges represents one of the most exciting and promising frontiers in astrophysics. These magnetic structures offer a unique window into the fundamental forces that shape the universe, from the behavior of galaxies to the interaction of dark matter and dark energy. As we continue to study these phenomena, we will not only gain a deeper understanding of magnetic fields but also uncover new insights into the workings of the universe itself. The journey into the heart of these cosmic bridges is only just beginning, and the discoveries ahead may be as vast and intricate as the universe they help to illuminate. As we continue our exploration of extragalactic magnetic bridges, it's essential to examine the future of research in this field. With new advancements in technology, our ability to observe and analyze these structures is advancing at an incredible rate. The next few decades will likely reveal more about the true nature of these magnetic phenomena, and it's possible that our current understanding of the universe will be reshaped in profound ways. One of the most exciting advancements is the continued development of radio astronomy. Magnetic fields, especially those in the extragalactic medium, emit radio waves that can be detected by specialized telescopes. The Square Kilometre Array, SKA, a next-generation radio telescope that will be constructed in South Africa and Australia, promises to be a game-changer in our understanding of the universe. The SKA will be able to map the sky with unprecedented detail, allowing scientists to study extragalactic magnetic fields with greater precision than ever before. This will provide valuable data on the structure and behavior of magnetic bridges, and potentially reveal new details about the interaction between galaxies, galaxy clusters, and the cosmic web. Another promising tool for studying extragalactic magnetic fields is the upcoming James Webb Space Telescope, JWST. While the JWST is primarily designed to study the infrared spectrum, its high-resolution imaging capabilities will also allow it to investigate the dynamics of galaxy clusters and the magnetic fields within them. The JWST's sensitivity to faint light from distant objects will help scientists probe regions of space that were previously inaccessible, giving us a clearer picture of the role magnetic fields play in the evolution of galaxies and clusters. But it's not just new telescopes that will drive our understanding forward. Computational astrophysics is also making huge strides, with powerful simulations helping scientists model the behavior of magnetic fields in extragalactic environments. These simulations allow researchers to test different theories and predictions about how magnetic fields affect the structure of galaxies and clusters. By combining observational data with these simulations, scientists will be able to create a more complete and nuanced picture of the cosmos. Simulations can also help us explore the more complex interactions between magnetic fields and other cosmic phenomena, such as supermassive black holes and relativistic jets, shedding light on the underlying mechanisms that drive these high-energy processes. Furthermore, advances in particle physics could play a significant role in enhancing our understanding of extragalactic magnetic bridges. High-energy cosmic particles, such as cosmic rays, are often accelerated by the strong magnetic fields in galaxy clusters and other extragalactic environments. By studying these particles and the processes by which they are accelerated, scientists can gain insights into the properties of magnetic fields and how they influence the behavior of matter in the universe. Research in this area is also closely tied to the study of dark matter and dark energy, as understanding the role of magnetic fields in these phenomena could provide crucial clues about the nature of these elusive substances. Despite all the progress being made, there are still many unanswered questions about extragalactic magnetic fields and their role in the universe. For example, while we know that magnetic fields are present in galaxy clusters and the cosmic web, the exact origin of these fields remains a mystery. Did they form during the Big Bang, or are they the result of later processes in the evolution of the universe? And how do these magnetic fields interact with the mysterious dark matter that makes up the majority of the universe's mass? These are just a few of the questions that scientists are currently grappling with, and as our tools and techniques improve, it is likely that we will get closer to answering them. Another fascinating aspect of extragalactic magnetic fields is their potential to influence the formation of life elsewhere in the universe. While magnetic fields on Earth play a crucial role in protecting our planet from harmful cosmic radiation, it is possible that similar magnetic structures could help shield other planets and distant galaxies. This raises the intriguing possibility that magnetic fields could play a key role in the habitability of exoplanets. If magnetic bridges help stabilize the cosmic web and facilitate the formation of stable, long-lived galaxies, it could increase the chances of life emerging elsewhere in the universe. As we continue to search for life beyond our solar system, understanding the role of magnetic fields in this process could be a critical piece of the puzzle. In a more speculative sense, the study of extragalactic magnetic fields might also offer insights into the ultimate fate of the universe. If magnetic fields are indeed involved in the expansion of the cosmos, they could provide clues about the long-term evolution of the universe and the nature of dark energy. Some theories suggest that the universe could eventually experience a big freeze, or heat death, where it expands forever, becoming colder and more diffuse over time. Magnetic fields could play a role in this process, either by influencing the distribution of matter or by interacting with dark energy in ways we don't yet fully understand. While this remains speculative, the study of extragalactic magnetic fields could offer new perspectives on the fate of the cosmos. Looking ahead, the next frontier in extragalactic magnetic field research may lie in the study of the most distant reaches of the universe. The further we look, the closer we get to the beginning of the universe itself. By studying the magnetic fields of distant galaxies and galaxy clusters, scientists may be able to probe the earliest moments of cosmic history, offering insights into the formation of the first structures in the universe. This could help us understand how galaxies and magnetic fields came into existence, shedding light on the fundamental processes that govern the evolution of the cosmos. The study of extragalactic magnetic bridges is one of the most exciting and rapidly advancing areas of modern astrophysics. These magnetic structures offer profound insights into the forces that shape the universe, from galaxy formation to the behavior of dark matter and dark energy. As our observational tools and computational models continue to improve, we will be able to delve even deeper into the mysteries of these cosmic phenomena. The discoveries that lie ahead promise to be as transformative as they are awe-inspiring, and the study of extragalactic magnetic fields may one day help us answer some of the most profound questions about the nature of the universe and our place within it. As we continue our exploration of extragalactic magnetic bridges, it's important to delve deeper into how these magnetic fields interact with the larger structure of the universe. These magnetic fields don't just exist in isolation. They are part of a grand cosmic network. The behavior of magnetic fields in the intergalactic medium is influenced by a variety of factors, including the dynamics of galaxy clusters, the flow of cosmic gas, and the intense forces exerted by supermassive black holes. Understanding how magnetic fields interact with these components is crucial in uncovering the deeper mechanics of cosmic evolution. In many ways, the study of extragalactic magnetic fields is similar to piecing together a cosmic puzzle. As we continue to observe these magnetic structures, we gain valuable insights into the underlying processes that drive the universe's evolution. One of the most fundamental questions in astrophysics is how galaxies, galaxy clusters, and even the intergalactic medium have formed over cosmic time. Magnetic fields, particularly those that exist on the scale of galaxy clusters and the cosmic web, likely played a key role in this process. They could have influenced the way matter clumped together, creating the galaxies and structures that we see today. The role of magnetic fields in galaxy formation is especially significant when we consider their interaction with cosmic gas. Intergalactic gas, often found in the space between galaxies and clusters, is a critical component in the formation and evolution of galaxies. Magnetic fields can influence the motion of this gas, guiding its flow and preventing it from dispersing too quickly. This means that magnetic fields might have helped to shape the very fabric of the universe, influencing the creation of galaxies and galaxy clusters. Another fascinating aspect of these magnetic structures is their connection to cosmic rays. Cosmic rays, high-energy particles that travel across vast distances in space, are thought to be accelerated by the strong magnetic fields present in galaxy clusters. These particles, which include protons and atomic nuclei, carry vast amounts of energy, and their behavior is influenced by the magnetic fields they encounter. By studying the interactions between cosmic rays and magnetic fields, scientists can gain a better understanding of the conditions within galaxy clusters and the broader extragalactic medium. One of the most mysterious aspects of extragalactic magnetic fields is their potential connection to dark matter. Dark matter, which makes up a significant portion of the universe's mass, remains one of the biggest unsolved mysteries in astrophysics. Some researchers believe that magnetic fields might play a role in the behavior of dark matter, potentially influencing its distribution and interactions. While this is still a speculative area of study, it highlights the complexity of the universe and the intricate relationships between different cosmic components. If magnetic fields do have a connection to dark matter, this could open up a whole new avenue of research that could provide critical clues to understanding one of the most fundamental substances in the cosmos. The potential role of magnetic fields in shaping the fate of galaxy clusters is another area of active research. Magnetic fields are not static; they evolve over time, influenced by the movement of gas, the rotation of galaxies, and the activity of supermassive black holes. Understanding how these magnetic fields change and evolve can offer insights into the long-term behavior of galaxy clusters. For example, the interactions between magnetic fields and the hot gas that pervades galaxy clusters could influence the cooling rates of these clusters, potentially affecting their overall growth and development. In addition to their role in galaxy clusters, extragalactic magnetic fields also influence the cosmic web, the large-scale structure of the universe. The cosmic web consists of vast filaments of gas and dark matter that connect galaxies and clusters of galaxies. Magnetic fields are believed to permeate this web, influencing the flow of matter and the development of galactic structures. The presence of these magnetic fields could provide a key to understanding the organization and evolution of the universe on the largest scales. As we look toward the future of extragalactic magnetic field research, it's clear that we are on the cusp of a new era in astrophysics. With advancements in both observational techniques and computational models, scientists are now able to probe the universe in ways that were previously unimaginable. New telescopes and instruments, such as the SKA and the JWST, promise to revolutionize our understanding of cosmic magnetic fields. These tools will allow us to study distant galaxies and galaxy clusters with unprecedented detail, offering new insights into the behavior of magnetic fields and their role in the evolution of the cosmos. Moreover, as our understanding of magnetic fields expands, it could have far-reaching implications for our understanding of other cosmic phenomena. For instance, the study of extragalactic magnetic fields could shed light on the nature of supermassive black holes, which are believed to be surrounded by powerful magnetic fields. By examining how these fields influence the behavior of matter near the event horizon, scientists may gain new insights into the workings of black holes and the processes that govern their growth and activity. In the context of galaxy evolution, magnetic fields might also help explain why certain galaxies exhibit unique characteristics. Some galaxies, for example, display unusual patterns of star formation, while others seem to be dead, with little or no ongoing star formation. Magnetic fields may play a key role in regulating these processes, either by inhibiting or enhancing the conditions required for star formation. Understanding these mechanisms could help us explain why some galaxies thrive while others stagnate. There is also the potential for magnetic fields to impact the evolution of life in the universe. While this may seem like a stretch, consider that magnetic fields on Earth play a vital role in protecting the planet from harmful cosmic radiation. If similar magnetic structures exist elsewhere in the universe, they could offer similar protection to exoplanets and distant star systems. This raises the tantalizing possibility that magnetic fields could play a crucial role in creating conditions conducive to life on other planets. If magnetic fields help shield planets from harmful radiation, they might enhance the habitability of exoplanets in ways we have not yet fully considered. Beyond their direct effects on galaxies and cosmic structures, extragalactic magnetic fields may also be influencing the expansion of the universe itself. The role of dark energy in this process is still not fully understood, but some theories suggest that magnetic fields could be interacting with dark energy in ways that influence the rate of cosmic expansion. While this idea is still in the realm of speculation, it highlights the interconnectedness of the universe and the potential for magnetic fields to play a role in some of the most profound questions about the nature of space and time. The study of extragalactic magnetic bridges is a fascinating and rapidly advancing field of research that holds the potential to reshape our understanding of the universe. These magnetic structures are not just passive features of the cosmos, they actively influence the formation and evolution of galaxies, clusters, and the intergalactic medium. As our observational tools and computational models continue to improve, we will uncover more about the behavior of magnetic fields and their impact on the broader cosmic landscape. Whether through their role in galaxy formation, their connection to dark matter, or their influence on the cosmic web, extragalactic magnetic fields offer a window into the deepest mysteries of the universe. As we continue to explore these phenomena, we will gain a better understanding of the forces that shape the cosmos and the origins of the structures we see today. The future of this research is incredibly exciting, and it promises to unveil even more incredible discoveries in the years to come. As we continue exploring the profound influence of extragalactic magnetic fields on the cosmos, we begin to understand that these invisible forces are deeply intertwined with the fundamental workings of the universe. These magnetic structures, stretching across vast distances between galaxies, are much more than mere curiosity. They are integral to the grand cosmic architecture. Magnetic bridges and their role in galaxy formation provide one of the most compelling areas of research. The nature of galaxy formation itself is influenced by the way gas and dust behave under the influence of magnetic fields. In many instances, galactic gas, especially within clusters, is trapped in long, winding magnetic fields that prevent it from dispersing too quickly. These magnetic bridges could very well act as cosmic highways, channeling gas between galaxies and helping to stabilize the material necessary for the formation of new stars. These long-range magnetic connections between galaxies and galaxy clusters may also play an essential role in maintaining the stability of cosmic structures. The magnetic forces can create a kind of cosmic web, where filaments of gas and matter are drawn together, forming the large-scale structures we observe in the universe today. Without the influence of these magnetic fields, these structures may have formed differently, or not at all. This intricate balance between gravitational forces and magnetic influence shapes the very large-scale structure of the universe, dictating where galaxies are located and how they interact with each other. One of the most intriguing aspects of extragalactic magnetic fields is their connection to the phenomenon of cosmic inflation, the rapid expansion of the universe that is believed to have occurred in the first moments after the Big Bang. While magnetic fields were not directly responsible for inflation, they may have played a role in shaping the universe during this period. The rapid expansion of space would have stretched out any pre-existing magnetic fields, and as the universe cooled, these fields became embedded in the fabric of the cosmos. The magnetic bridges we observe today may be relics of this ancient cosmic expansion, remnants of the universe's early conditions. Additionally, the interplay between these magnetic structures and dark matter remains a tantalizing mystery. Dark matter, which makes up about 27% of the universe's mass, has yet to be fully understood. Magnetic fields, in theory, could interact with dark matter in ways we have yet to uncover. If magnetic fields are, indeed, influencing dark matter, they may be playing a significant role in the behavior and distribution of this elusive substance. Could it be that these magnetic fields are shaping the way dark matter is distributed across the universe, or even how it interacts with visible matter? While we are far from answering these questions definitively, the potential for magnetic fields to unlock the mysteries of dark matter makes this an exciting area of research. As we turn our attention to the behavior of cosmic rays, it's clear that magnetic fields serve as a guide for these high-energy particles. Cosmic rays, which originate from some of the most violent and energetic processes in the universe, interact with magnetic fields on their journey through space. The magnetic bridges stretching between galaxies and galaxy clusters act as guiding structures, steering these particles across vast distances. By studying the movement and acceleration of cosmic rays, scientists are learning more about the conditions within galaxy clusters and the environments of extragalactic space. Magnetic fields also play a significant role in the activity surrounding supermassive black holes, which reside at the centers of most galaxies. These black holes are surrounded by powerful magnetic fields, which play a vital role in the behavior of the surrounding accretion disks. The accretion disks, made up of gas and dust being pulled toward the black hole, are intensely hot and energetic. The magnetic fields present in these regions help channel the flow of matter and energy, potentially influencing the formation of relativistic jets, highly energetic beams of particles that shoot out from the poles of the black hole at nearly the speed of light. The relationship between magnetic fields and supermassive black holes is a fascinating and complex one, and studying these interactions provides insight into some of the most extreme environments in the universe. The role of magnetic fields extends beyond just galaxy clusters and supermassive black holes. Even in the vast spaces between galaxies, the magnetic fields play a role in the dynamics of the intergalactic medium. This empty space, which is far from being devoid of matter, is home to a variety of gas clouds, some of which can be traced by their magnetic fields. These fields may not only help in the movement of gases but could also influence the processes of galaxy formation in ways we have yet to fully understand. By studying the magnetic bridges that connect galaxies and the intergalactic medium, researchers are uncovering clues to the complex processes that govern the universe's largest structures. One of the most exciting possibilities on the horizon is the development of new observational tools, such as the Square Kilometre Array, SK, which will allow us to map the magnetic fields across the entire universe with unprecedented precision. This global network of radio telescopes, spread across vast distances on Earth, promises to revolutionize our understanding of cosmic magnetism. With the SKA, scientists will be able to observe the intricate details of magnetic structures across extragalactic space, gaining insights into their role in everything from galaxy formation to the behavior of high-energy cosmic particles. The future of extragalactic magnetic field research also lies in our ability to model the behavior of these fields. Using complex computer simulations, researchers are creating models that mimic the dynamics of magnetic fields in various cosmic environments. These simulations allow scientists to test hypotheses about how magnetic fields influence galaxies, clusters, and the intergalactic medium, and they provide valuable insight into the physics that govern the universe at large. As our computing power continues to increase, these models will become more sophisticated, offering increasingly accurate predictions about the role of magnetic fields in the universe. Moreover, the study of extragalactic magnetic fields has profound implications for our understanding of the universe's evolution. By examining how these magnetic fields have changed over cosmic time, we can gain insights into the processes that shape the universe as we know it. These fields may hold the key to understanding how matter was distributed in the early universe, how galaxies formed, and how they continue to evolve. The magnetic bridges between galaxies and galaxy clusters might hold vital information about the growth and development of cosmic structures and the forces that have shaped the universe over billions of years. The link between magnetic fields and the cosmic web, the vast network of interconnected filaments that spans the universe, is another critical area of study. The cosmic web itself is a massive structure, made up of vast filaments of dark matter and gas, connecting galaxies and clusters of galaxies. Magnetic fields play a role in the behavior of this web, influencing how matter flows through it, and how galaxies interact with one another. The presence of magnetic fields in the cosmic web could also help explain the large-scale organization of the universe, providing valuable insight into the processes that shape the universe's largest structures. In addition to their scientific significance, the study of extragalactic magnetic fields could have far-reaching technological implications. Understanding how magnetic fields affect the movement of charged particles across space could lead to advancements in technology here on Earth. For example, understanding how magnetic fields influence the behavior of plasma could help improve our understanding of fusion energy, a potential future source of clean power. Magnetic fields also play a role in the operation of various technologies. By exploring the nature of extragalactic magnetic fields, we may uncover new principles that could be applied to the development of innovative technologies. Extragalactic magnetic bridges are more than just fascinating cosmic phenomena. They are vital components of the universe's larger structure and evolution. From shaping the formation of galaxies to guiding cosmic rays, these magnetic fields play a fundamental role in the dynamics of the cosmos. As we continue to explore these magnetic structures, we unlock new insights into the history and future of the universe. The study of these fields is not only essential for understanding the universe's past but also for understanding the forces that will shape its future. With each new discovery, we inch closer to unraveling the mysteries of the universe and uncovering the profound forces that govern it. As we continue our exploration of extragalactic magnetic bridges, we begin to realize that these phenomena are far more complex than initially anticipated. Beyond their role in galaxy formation and the cosmic web, these magnetic fields are intertwined with a number of other fundamental processes that influence the evolution of the universe on a grand scale. They challenge our traditional understanding of the cosmos and offer us new insights into some of the universe's most profound mysteries. One of the most fascinating aspects of these magnetic fields is their influence on the behavior of high-energy particles, particularly in the context of cosmic ray propagation. Cosmic rays are subatomic particles that travel through space at nearly the speed of light, originating from some of the most energetic and explosive events in the universe, such as supernovae and active galactic nuclei. These particles interact with the magnetic fields in extragalactic space, and their movement is heavily influenced by these fields as they travel across vast distances. Cosmic rays can be deflected and even trapped by magnetic fields, causing them to follow complex, curved paths across the universe. This behavior has significant implications for our understanding of how cosmic rays are accelerated and how they propagate. For example, when cosmic rays pass through regions of intense magnetic fields, such as those found in galaxy clusters or near supermassive black holes, they can be redirected or even concentrated. This process helps us understand the distribution and intensity of cosmic rays across the universe and provides us with valuable information about the environments where these particles are accelerated. Additionally, magnetic fields influence the behavior of the particles in other ways. For instance, when cosmic rays interact with magnetic fields, they can emit radiation in the form of synchrotron radiation. This high-energy radiation is a crucial tool for astronomers, as it allows them to study the properties of the magnetic fields and the particles themselves. The study of synchrotron radiation also provides us with a window into the most extreme environments in the universe, such as the regions around black holes and the cores of galaxies. Moreover, extragalactic magnetic fields are not static. They evolve over time, influenced by a variety of factors. These factors include the movement of matter, the formation of new structures, and even the gravitational influence of nearby objects. As the universe continues to expand and evolve, these magnetic fields are shaped by the complex interplay between matter and energy. This ongoing evolution presents both challenges and opportunities for scientists seeking to understand the true nature of these fields and their role in the cosmos. In terms of their long-term evolution, extragalactic magnetic fields may hold the key to understanding the universe's past and future. The interactions between magnetic fields and the large-scale structures of the universe are complex and multifaceted, but they may offer valuable clues about the forces that have shaped the cosmos over billions of years. For instance, by studying the way magnetic fields interact with the cosmic web, we can gain insights into the conditions that prevailed in the early universe and how these conditions led to the formation of galaxies, clusters, and other large-scale structures. Furthermore, the study of these magnetic fields is not limited to theoretical models or distant observations. With advancements in technology and observational techniques, we are now able to detect and study these fields in greater detail than ever before. Radio telescopes, for example, can capture the faint signals emitted by magnetic fields, allowing scientists to map these fields across vast regions of space. Observatories like the Event Horizon Telescope, EHT, which captured the first image of a black hole, are also contributing to this growing body of knowledge, providing us with more detailed views of the regions around supermassive black holes and the magnetic fields that influence their behavior. The future of extragalactic magnetic field research is incredibly promising. With the development of new and more sensitive instruments, scientists are poised to make groundbreaking discoveries that will deepen our understanding of the universe. For example, upcoming space missions, such as the James Webb Space Telescope, JWST, are expected to provide even more detailed observations of distant galaxies and their magnetic fields. These advancements in observational technology will not only help us map the cosmic magnetic landscape but also allow us to investigate how these fields influence the behavior of matter and energy across the universe. Additionally, the study of extragalactic magnetic fields could lead to new discoveries in fundamental physics. Magnetic fields play a central role in many aspects of physics, from electromagnetism to plasma dynamics, and understanding their behavior in the context of the cosmos could shed light on some of the most pressing questions in modern science. For instance, the relationship between magnetic fields and dark matter remains an open question. If magnetic fields are indeed interacting with dark matter in ways we don't yet understand, this could have profound implications for our understanding of this mysterious substance and its role in the evolution of the universe. Another exciting avenue of research lies in the study of magnetic fields and their connection to dark energy. Dark energy, which makes up approximately 68% of the universe's total energy content, is responsible for the accelerated expansion of the universe. While we know little about the true nature of dark energy, it is possible that magnetic fields could interact with it in ways that we have yet to discover. The influence of magnetic fields on the expansion of the universe could offer important insights into the behavior of dark energy, and how it will continue to shape the fate of the cosmos. In the context of galaxy evolution, magnetic fields may play a key role in the formation and growth of supermassive black holes. These black holes, which reside at the centers of most large galaxies, are some of the most mysterious and powerful objects in the universe. Their growth and activity are influenced by a number of factors, including the magnetic fields in their surroundings. The accretion disks surrounding supermassive black holes are often highly magnetized, and these magnetic fields help to channel the flow of gas and dust into the black hole. The interaction between magnetic fields and these disks also plays a role in the formation of relativistic jets, which are beams of high-energy particles that shoot out from the poles of the black hole. These jets are among the most energetic phenomena in the universe, and studying them can provide us with valuable insights into the physics of black holes and the magnetic fields that surround them. The broader implications of extragalactic magnetic fields extend beyond their influence on the large-scale structure of the universe. The study of these fields can also provide us with a deeper understanding of the fundamental forces that govern the cosmos. By exploring how magnetic fields interact with matter and energy, we can gain new insights into the nature of the universe itself, including its origins, its ongoing evolution, and its eventual fate. In this sense, the study of extragalactic magnetic fields is not just about understanding one particular phenomenon. It is about uncovering the deeper, hidden forces that shape the entire cosmos. As we look toward the future, one thing is certain: the study of extragalactic magnetic bridges and the role of magnetic fields in the universe is far from over. With new technologies, more sensitive instruments, and a growing body of research, we are on the cusp of discovering even more about these fascinating cosmic structures. Whether it's understanding the behavior of cosmic rays, uncovering the mysteries of dark matter and dark energy, or studying the formation of galaxies and black holes, the research into extragalactic magnetic fields will continue to illuminate the fundamental workings of the universe and our place within it. As we continue our deep dive into the complexities of extragalactic magnetic bridges, we find ourselves examining even more profound and far-reaching questions about the very nature of the universe. The interconnectedness of magnetic fields stretching across galaxies provides an opportunity to explore some of the most mind-bending questions in astrophysics. While we have touched on the role of these magnetic structures in cosmic rays, black holes, and galaxy evolution, there's so much more we can uncover by looking deeper into how these magnetic fields function and evolve on cosmological scales. One of the most intriguing aspects of extragalactic magnetic fields is their potential connection to cosmic inflation. The theory of cosmic inflation suggests that in the earliest moments of the universe, it expanded exponentially at an unimaginable rate, smoothing out the distribution of matter and energy. Some scientists speculate that magnetic fields could have played a role during this phase of rapid expansion. The presence of large-scale magnetic fields could have influenced the formation of structures in the universe, shaping the way galaxies, clusters, and cosmic voids developed over billions of years. It is also possible that these magnetic fields were a byproduct of the intense conditions during the birth of the universe. As the universe cooled and matter began to form into distinct structures, magnetic fields could have been generated through processes like turbulence, the motion of charged particles, and the expansion of space itself. These fields could have been imprinted on the very fabric of the cosmos during the Big Bang, providing a lasting trace of the universe's earliest moments that we can still study today. Understanding the connection between these magnetic fields and cosmic inflation is no small task. It requires us to venture into some of the most challenging areas of modern physics, including the study of quantum mechanics, general relativity, and the nature of spacetime. As we push the boundaries of our knowledge, it's clear that magnetic fields will play an essential role in unlocking these mysteries. Future experiments and simulations may provide the key to understanding how these fields originated, how they evolved, and how they shape the universe we observe today. Another critical area of research revolves around the role of extragalactic magnetic fields in the formation of large-scale cosmic structures. The magnetic bridges we observe between galaxies aren't just passive features. They actively interact with the material surrounding them. The impact of magnetic fields on the formation of galaxy clusters, for instance, is an area of intense study. In these clusters, magnetic fields can influence the movement of hot gas, contributing to the way galaxies interact with one another. One fascinating phenomenon related to this interaction is the creation of galactic filaments. These vast structures of interconnected galaxies stretch across millions of light years and form the backbone of the cosmic web. It is thought that magnetic fields may help guide the formation of these filaments, influencing the distribution of dark matter and the gas that forms the galaxies themselves. By studying how magnetic fields interact with these large-scale structures, we may gain valuable insights into the forces that govern the formation and growth of galaxies. On a smaller scale, magnetic fields also play a critical role in the formation of stars. While the connection between magnetic fields and star formation is better understood within our own Milky Way galaxy, the same principles are believed to apply to extragalactic environments. Magnetic fields can affect the flow of gas in molecular clouds, influencing how these clouds collapse to form new stars. In some cases, magnetic fields can even prevent the collapse of certain regions within a cloud, effectively regulating the rate at which stars are born. This delicate balance between the forces of gravity, pressure, and magnetic fields is key to understanding star formation not only in our galaxy but in galaxies across the universe. Magnetic fields also have an essential role in the process of galactic feedback, which refers to the way energy from stars and black holes can affect the surrounding environment. Feedback mechanisms, such as the energy released by supernovae and active galactic nuclei, can help shape the structure and evolution of galaxies. These processes are often influenced by the magnetic fields within and around galaxies. For instance, powerful jets of particles from supermassive black holes can interact with magnetic fields, affecting the distribution of gas and energy in the galaxy. The study of these feedback mechanisms is crucial to understanding how galaxies evolve over time, and how they are shaped by the energetic processes occurring within them. In addition to their impact on individual galaxies, extragalactic magnetic fields also influence the intergalactic medium, the vast, nearly empty space between galaxies. This medium, composed of hot, ionized gas, plays a crucial role in the dynamics of galaxy clusters. Magnetic fields in the intergalactic medium can regulate the movement of gas between galaxies, influencing the rate of star formation and the distribution of matter in these clusters. In some cases, these fields can even help stabilize the hot gas in galaxy clusters, preventing it from dispersing and aiding in the overall structure of the cluster. The effect of magnetic fields on the intergalactic medium also extends to the phenomenon known as the Sunyaev-Zeldovich effect, which occurs when cosmic microwave background radiation interacts with high-energy electrons in the intracluster medium. The presence of magnetic fields in these regions can influence the intensity and distribution of this radiation, providing astronomers with another valuable tool for studying galaxy clusters and their magnetic environments. By studying how magnetic fields affect the Sunyaev-Zeldovich effect, scientists can gain insights into the properties of the intergalactic medium and how it has evolved over time. As we dig deeper into the research on extragalactic magnetic fields, we begin to realize that they are not isolated phenomena but rather interconnected with many other aspects of the cosmos. Their presence and influence extend across the vast reaches of space, shaping the environments of galaxies, clusters, and even the dark voids that separate them. By studying these fields, we are not only learning about the structures and behaviors of individual galaxies but also gaining a deeper understanding of the fundamental forces that govern the universe. One of the challenges in studying extragalactic magnetic fields is their faintness and the difficulty in detecting them. Unlike other forms of radiation, such as visible light or X-rays, magnetic fields do not emit light directly. Instead, we must rely on indirect methods to detect their presence and measure their strength. One such method involves the study of synchrotron radiation, which is emitted by charged particles moving through magnetic fields. By observing the patterns of this radiation, astronomers can map the magnetic fields in distant galaxies and clusters, giving us a glimpse into the unseen forces that shape the cosmos. Another challenge lies in the sheer scale of the structures we are studying. Extragalactic magnetic fields span vast distances, often stretching across millions of light years. This means that the fields we are observing are not just local phenomena but part of a much larger, interconnected cosmic network. Mapping these fields requires the use of powerful telescopes and advanced computational models, both of which are continuously improving as technology advances. With new instruments like the Square Kilometre Array, SKA, and future space-based observatories, we are poised to make groundbreaking discoveries about the nature of these magnetic fields and their role in the universe. Looking ahead, the future of extragalactic magnetic field research is incredibly exciting. The more we learn about these cosmic bridges, the more we realize how integral they are to our understanding of the universe. From influencing the behavior of high-energy particles to shaping the formation of galaxies, magnetic fields play a central role in the evolution of the cosmos. As we continue to explore their mysteries, we will undoubtedly uncover new insights that challenge our understanding of the universe's origins and its ultimate fate. The study of extragalactic magnetic fields not only deepens our knowledge of the cosmos but also raises profound questions about the very nature of reality itself. What are the fundamental forces that govern the universe, and how do they interact to create the vast and intricate structures we observe? How do magnetic fields influence the flow of time and space, and what can they tell us about the origins and ultimate destiny of the universe? These questions, and many more, lie at the heart of the ongoing exploration of extragalactic magnetic fields. The study of extragalactic magnetic fields continues to be one of the most intriguing and complex areas of modern astrophysics. As we delve further into this subject, we encounter not only the challenges of detecting these invisible forces but also the opportunity to unlock some of the universe's greatest mysteries. Through observations and models, scientists are working tirelessly to decipher the complex role that magnetic fields play in shaping the cosmos. One aspect that we must consider in this ongoing exploration is the nature of cosmic magnetic fields on a universal scale. While we have primarily focused on extragalactic magnetic bridges and their influence within galaxy clusters and cosmic filaments, these fields also serve as a key player in the broader context of the universe's evolution. The distribution of magnetic fields on a large scale, across superclusters, voids, and other enormous structures, can reveal essential information about the initial conditions of the universe and the forces that shaped its evolution from the very beginning. Interestingly, some scientists propose that the large-scale magnetic fields we see today could be remnants of primordial fields generated during the early moments of the Big Bang. These fields, though faint and dispersed, could have influenced the distribution of matter and energy in the early universe, seeding the formation of galaxies and clusters. Their existence may be a key to understanding the cosmic evolution that led to the structure we observe in the universe today. Additionally, as we study magnetic fields at the extragalactic level, it becomes clear that their role extends far beyond the mere influence on individual galaxies or clusters. Magnetic fields have the potential to act as cosmic wires, connecting distant parts of the universe and enabling the transmission of energy across vast stretches of space. Just as electrical wires allow currents to flow and power machines, These cosmic magnetic fields could transmit energy between distant galaxies, acting as the backbone of energy transfer across the cosmos. The intriguing idea of magnetic energy highways, or cosmic energy transmission systems, stretches the imagination. As research on this topic progresses, astronomers and physicists are beginning to explore whether these magnetic fields could play a role in energy exchange not only within galaxy clusters but across vast cosmic distances. The possibility that magnetic fields allow for the movement of energy in ways we do not yet fully understand may revolutionize our understanding of the cosmos and how energy propagates on a grand scale. At the heart of many of these investigations lies the pursuit of understanding how magnetic fields evolve and interact across the immense expanses of space. The magnetic fields we see in galaxies, while largely stable, are not static. They evolve and change over time, shaped by the forces acting on them, such as the motion of charged particles, supernovae explosions, and the activity of supermassive black holes. These fields can twist and wind themselves into intricate patterns, creating complex structures within galaxies and clusters that have an immense impact on the behavior of cosmic matter. The winds from stars, the jets from black holes, and even the outflows from supernovae can stretch and distort the magnetic fields in a galaxy. The intergalactic medium, in turn, responds to these magnetic fields, which can amplify or diminish the flow of gas within a galaxy cluster. This constant process of magnetic evolution shapes the behavior of galaxies over time, influencing star formation, the movement of gas, and even the creation of new cosmic structures. It's not just the visible structures that matter. The invisible magnetic fields may be shaping much of the underlying dynamics of galaxies, stars, and clusters. Looking at more localized phenomena within these regions, we can also observe how individual galaxies themselves are shaped by their magnetic environments. Our own Milky Way, for instance, has a well-defined magnetic field that influences its spiral structure and star formation. This field interacts with the interstellar medium, channeling and controlling the flow of ionized gas that makes up the galaxy's arms. However, the magnetic fields of other galaxies may differ in their strength, structure, and influence on local environments. Some galaxies have been observed to possess particularly strong magnetic fields, which might play a role in their evolution or even their survival in a hostile cosmic environment. But the influence of these magnetic fields doesn't stop at the boundaries of individual galaxies or galaxy clusters. As we move beyond, into the larger-scale structures of the universe, we begin to see that these fields play a role in the movement and distribution of cosmic particles, cosmic rays, and high-energy radiation. Some of these fields can stretch over vast distances, connecting distant galaxies across the vast cosmic voids that separate them. These magnetic bridges, so to speak, may be responsible for the flow of energetic particles across the intergalactic medium, affecting how these particles are distributed across the universe. Such long-range effects give rise to another critical area of research: cosmic rays. These high-energy particles, which include protons and atomic nuclei, travel vast distances through space, often originating from distant galaxies, supernova remnants, or even active galactic nuclei. Magnetic fields play a crucial role in the behavior and travel of cosmic rays, as they can bend the path of these particles and influence their speed. Understanding how magnetic fields in the extragalactic realm interact with cosmic rays can provide critical insight into the origins of these particles and the forces that guide their journey through the universe. Moreover, extragalactic magnetic fields are essential in the study of high-energy astrophysics. As we continue to study energetic phenomena like gamma-ray bursts, the most powerful explosions known to occur in the universe, we find that magnetic fields are central to their dynamics. These fields likely play a significant role in the acceleration of particles to relativistic speeds, creating the conditions necessary for such extreme events. Whether through the formation of jets or the interaction of magnetic fields with plasma in the vicinity of black holes, magnetic fields provide the energy and structure needed to produce these intense bursts of radiation. One exciting area of research lies in understanding how these extreme environments, around black holes, supernova remnants, and active galactic nuclei, generate such intense magnetic fields. Some of the most powerful magnetic fields in the universe exist in these regions, with strengths far beyond anything we encounter in more tranquil parts of space. The mechanisms behind the generation of these fields are complex and may involve processes like the motion of conducting plasma, the twisting of magnetic field lines due to rotating black holes, and the interaction of charged particles within these high-energy environments. Scientists are continuing to explore whether the extreme magnetic fields found in these regions have any connection to the magnetic fields observed on a galactic scale. Could the magnetic fields seen in distant galaxies be influenced by these powerful cosmic events? Are there ways in which the intense fields surrounding black holes and supernovae can affect the larger-scale cosmic magnetic network? These are the questions that scientists hope to answer in the coming years. It's worth noting that studying extragalactic magnetic fields is not just about understanding the structure and evolution of galaxies and clusters. It's also about the larger philosophical and fundamental questions about the universe. As we peel back the layers of complexity surrounding these fields, we encounter the possibility that these magnetic forces are, in fact, a fundamental part of the fabric of spacetime itself. They may represent one of the key components that shape the way the universe works on a cosmic scale, influencing not only the movement of matter but also the fundamental forces that govern all phenomena in the universe. These cosmic fields may hold the answers to some of the deepest questions about the origins and ultimate fate of the universe. If we can unlock their secrets, we may come closer to understanding the fundamental workings of the cosmos, how galaxies form, how they interact, and how the universe evolves from one moment to the next. Extragalactic magnetic bridges may hold the key to understanding the universe's past, present, and future in ways that we are only beginning to imagine. As we continue to explore the intricacies of extragalactic magnetic bridges and fields, it's important to understand that these cosmic phenomena not only provide insight into the dynamics of individual galaxies and clusters but also offer a unique perspective on the interconnectedness of the universe. Magnetic fields may act as a universal connective tissue, linking distant galaxies, clusters, and even voids, forming a vast, invisible network that stretches across the cosmos. This network, although challenging to study directly, serves as a bridge, literally and metaphorically, between different regions of the universe. The idea of cosmic connectivity through magnetic fields expands our understanding of the universe's structure. Magnetic bridges and the webs of influence that these fields form across galactic structures and voids may be more than just a local interaction. They might be the means by which information, energy, and matter are exchanged throughout vast regions of space. The potential role of these magnetic forces in creating or preserving the structure of the cosmos as a whole is a topic of growing interest in the field of extragalactic astrophysics. One area that is particularly fascinating is the role of extragalactic magnetic fields in the creation and maintenance of cosmic voids. These voids, which are vast regions of space largely devoid of matter, represent some of the largest structures in the universe. However, despite their lack of visible matter, they are not empty in the truest sense of the word. In these voids, faint magnetic fields still persist, shaping the gas and cosmic rays that move through them. These fields may have significant implications for the movement of matter across these voids and could influence the growth and evolution of cosmic structures by guiding the formation of galaxies at their boundaries. In addition to magnetic fields and voids, it's also important to consider their potential role in the interaction between galaxies. Many of the most intriguing phenomena in astronomy, such as galaxy mergers, supermassive black hole formation, and the development of active galactic nuclei, AGN, are influenced by magnetic fields. For example, in galaxy mergers, the magnetic fields of the colliding galaxies can interact in complex ways, creating powerful shocks and turbulence that affect the dynamics of star formation and the movement of gas. These magnetic fields could serve as a driving force in these mergers, amplifying the turbulence and guiding the flow of gas toward the center of the newly formed galactic structure. The dynamics of AGN are also highly influenced by magnetic fields. Supermassive black holes, which reside at the centers of most large galaxies, often have strong magnetic fields associated with them. These fields can accelerate charged particles to near-light speeds, creating powerful jets that extend far beyond the galactic core. These jets are often observed in the form of radio lobes or X-ray emissions, providing astronomers with a way to study these phenomena from great distances. The magnetic fields in these regions also play a role in shaping the accretion disks around the black holes, which are the regions of matter that are pulled into the black hole's gravitational grip. These magnetic fields can regulate the flow of matter in the accretion disk, affecting the rate at which matter is consumed by the black hole and even contributing to the release of energy that powers the AGN. Magnetic fields also influence the behavior of the intergalactic medium, the diffuse gas that exists between galaxies. This medium, which makes up much of the matter in the universe, is not empty but instead contains low-density gas, cosmic rays, and magnetic fields. These fields can guide the movement of gas, regulate the formation of new stars, and even influence the behavior of supernovae and other high-energy events. Magnetic fields can also help to stabilize the intergalactic medium, preventing it from becoming too turbulent and disrupting the formation of galaxies and clusters. In this sense, they act as a stabilizing force, maintaining the delicate balance that allows galaxies to form and evolve over time. One intriguing possibility is that extragalactic magnetic fields may also play a role in the process of cosmic inflation, the rapid expansion of the universe that occurred during its early moments. During inflation, the universe expanded exponentially in a fraction of a second, and it's thought that magnetic fields could have played a part in this process, either by amplifying the energy fluctuations that drove inflation or by influencing the way that matter and energy were distributed throughout the universe. If these fields were indeed present during inflation, their remnants could still be detectable today, providing valuable clues about the very early universe. As we continue to observe the universe, one of the most exciting aspects of studying extragalactic magnetic fields is the potential for discovering new and unexpected phenomena. Magnetic fields, though invisible to the naked eye, leave their mark on the cosmos in ways that we are only beginning to understand. From the creation of cosmic bridges to the influence they exert over the movement of gas, the formation of stars, and the behavior of galaxies, magnetic fields are integral to the universe's functioning. One of the most significant challenges in studying extragalactic magnetic fields is their faintness. These fields are often incredibly weak and diffuse, making them difficult to detect with traditional observational techniques. However, advancements in technology are allowing astronomers to study these fields in increasingly sophisticated ways. Instruments such as radio telescopes and polarimeters are enabling scientists to measure the polarization of light coming from distant galaxies, providing clues about the strength and orientation of magnetic fields. By observing the way that light interacts with magnetic fields, astronomers can infer the presence of these fields even if they are too faint to be directly observed. In addition to these observational techniques, theoretical models are also playing a crucial role in advancing our understanding of extragalactic magnetic fields. These models, which simulate the behavior of magnetic fields in different cosmic environments, are essential for interpreting the data we gather from observations. By comparing theoretical predictions with observational results, scientists can refine their models and develop a more accurate picture of how these fields influence the universe. One of the most exciting areas of future research is the potential for studying the magnetic fields of distant galaxies and clusters in real time. As technology continues to improve, astronomers will be able to observe these fields with greater precision and over longer periods, allowing them to track changes in the magnetic environment of galaxies and clusters. This could provide valuable insights into the evolution of magnetic fields and their role in the ongoing dynamics of the universe. Ultimately, the study of extragalactic magnetic bridges is not just about understanding the forces that shape galaxies and clusters, but also about uncovering the deeper, more fundamental truths of the universe itself. Magnetic fields, as invisible as they may hold the key to understanding the cosmic web that underpins all of reality. As we continue to study these magnetic forces and unravel their mysteries, we may come closer to understanding the very nature of the universe, its origins, its structure, and its ultimate fate. The exploration of extragalactic magnetic fields and bridges continues to uncover increasingly complex and profound insights about the structure and dynamics of the cosmos. As we delve deeper into this fascinating area of research, we start to realize that these invisible forces not only shape the galaxies and stars we observe, but they may also offer a glimpse into the very processes that govern the universe itself. The study of extragalactic magnetic fields and their associated phenomena is far from a niche subject. It is an essential piece of the puzzle that allows us to understand cosmic evolution on a large scale. One of the most exciting aspects of this field is the discovery of magnetic fields that extend well beyond the galaxies themselves. While it's been known for some time that individual galaxies possess magnetic fields, the concept of a cosmic web of magnetic fields that stretches across vast intergalactic distances is a relatively new one. This realization has profound implications for our understanding of the large-scale structure of the universe. If magnetic fields can bridge the gaps between galaxies and even entire galaxy clusters, it suggests a level of interconnectedness across the universe that was previously unimaginable. These fields could, in theory, act as cosmic highways, enabling the exchange of energy, matter, and information over distances that span billions of light-years. The idea of magnetic bridges connecting distant regions of space raises fundamental questions about the nature of space-time itself. Magnetic fields are typically associated with the presence of charged particles, and in the case of these vast extragalactic bridges, the movement of these particles through magnetic fields could potentially create ripples in space-time, similar to the way gravitational waves are produced by the movement of massive objects. This opens up the possibility that the study of extragalactic magnetic fields might offer an entirely new way to probe the fabric of space-time and investigate phenomena like dark matter and dark energy. Magnetic fields, though relatively weak compared to gravitational forces, might still have a significant role to play in shaping the universe on the largest scales. While the effects of extragalactic magnetic fields are still not fully understood, some theorists speculate that they may help to explain certain enigmatic phenomena observed in the distant universe. For example, the polarization of light emitted by distant galaxies and quasars can provide clues about the strength and orientation of magnetic fields over vast distances. In some cases, astronomers have observed unexpected patterns in the polarization of light, suggesting the presence of magnetic fields that stretch across entire galaxy clusters or even larger cosmic structures. These observations are still being studied, but they could one day reveal how these magnetic fields influence the movement of galaxies, the formation of stars, and even the behavior of supermassive black holes. In addition to their potential role in shaping large-scale structures, extragalactic magnetic fields may also provide a key to understanding the formation and evolution of galaxies themselves. Magnetic fields have been shown to play a significant role in the process of star formation, as they can affect the collapse of gas clouds and regulate the flow of matter within galaxies. By studying how these fields behave in different cosmic environments, astronomers may be able to gain new insights into the conditions that lead to the birth of stars and galaxies. This research is still in its early stages, but it's an area that holds tremendous potential for advancing our understanding of galaxy formation on the largest scales. Furthermore, magnetic fields are thought to be intricately linked to the behavior of black holes, particularly the supermassive black holes at the centers of many galaxies. These black holes are surrounded by accretion disks, vast swirling masses of gas and dust that are pulled toward the black hole by its immense gravity. Magnetic fields play a crucial role in regulating the flow of matter within these disks, and in some cases, they can even help to channel material away from the black hole in powerful jets of relativistic particles. These jets can extend for millions of light-years and have a profound impact on the surrounding galaxy, heating gas, and preventing star formation in certain regions. Understanding how magnetic fields influence the behavior of these black hole jets could provide critical insights into the dynamics of supermassive black holes and their role in the evolution of galaxies. In terms of practical applications, the study of extragalactic magnetic fields also has the potential to impact the field of astrophysics on a technological level. For example, as astronomers continue to refine their methods of observing distant cosmic objects, the ability to detect and measure the polarization of light can provide unprecedented levels of detail about the magnetic environments surrounding galaxies, clusters, and black holes. These observational techniques could lead to the development of new technologies capable of detecting and mapping magnetic fields across large regions of space with greater accuracy. The ability to map out these fields in 3D across entire galaxy clusters could revolutionize our understanding of cosmic dynamics and lead to new breakthroughs in our ability to model the universe as a whole. Theoretical models that describe the behavior of extragalactic magnetic fields are constantly evolving, and new breakthroughs in the field of computational astrophysics are enabling scientists to simulate the interactions between magnetic fields and various cosmic phenomena in increasingly sophisticated ways. These models not only allow us to test hypotheses about how magnetic fields affect the formation and evolution of galaxies, but they also provide a platform for exploring new theories about the role of magnetism in the universe. As these models become more advanced, they could provide answers to some of the most profound questions in astrophysics, such as the nature of dark matter and dark energy, or the true structure of the universe on the largest scales. Looking ahead, the study of extragalactic magnetic fields will likely continue to evolve in exciting and unexpected ways. With the advent of next-generation telescopes and advanced observational techniques, we are now able to study the universe with a level of precision that was previously unimaginable. Instruments such as the Square Kilometre Array, which will be capable of observing the sky in unprecedented detail at radio wavelengths, could play a crucial role in mapping out the magnetic structures that stretch across the cosmos. This, in turn, could lead to new discoveries about the origin and evolution of the universe itself, as well as our place within it. The study of extragalactic magnetic bridges and fields is an exciting and rapidly evolving area of astrophysics that has the potential to reshape our understanding of the universe. From their role in shaping large-scale cosmic structures to their influence on the behavior of galaxies, black holes, and intergalactic matter, magnetic fields are central to many of the most fundamental processes in the cosmos. As we continue to explore the vast expanse of space, we are only beginning to scratch the surface of the mysteries that these invisible forces hold. The study of extragalactic magnetic fields may one day provide the key to unlocking some of the deepest secrets of the universe, offering insights into everything from the nature of dark matter to the fundamental laws of physics that govern the cosmos. As we continue to explore the topic of extragalactic magnetic bridges and their far-reaching implications, it becomes clear that these magnetic fields are not just isolated phenomena. They form an essential part of the cosmic ecosystem. By linking different regions of the universe, these magnetic structures may be involved in processes that go beyond simple gravitational interactions. They could be a driving force in the broader context of cosmic evolution, helping to shape the properties of galaxies and clusters over vast periods of time. One of the fascinating aspects of these magnetic fields is their potential to influence the behavior of cosmic jets. We've seen how supermassive black holes can shoot out vast jets of plasma at nearly the speed of light. But what if these jets are, in part, influenced or even shaped by the extragalactic magnetic fields we are discussing? Understanding the interaction between magnetic fields and these high-energy jets might shed light on the mechanisms behind some of the most energetic phenomena in the universe. For example, could magnetic fields help guide the direction of these jets, or could they contribute to their acceleration? Another aspect of extragalactic magnetic fields that is still poorly understood is their potential interaction with cosmic rays. These high-energy particles, primarily composed of protons and atomic nuclei, constantly bombard the Earth and the rest of the universe. Magnetic fields are thought to play a role in accelerating these particles, and it's possible that extragalactic magnetic fields could influence the behavior of cosmic rays in ways that we are only beginning to understand. Some theorists propose that these fields may accelerate particles to energies beyond anything achievable through known mechanisms in individual galaxies. This connection between magnetic fields and cosmic ray acceleration could open up new avenues for research, especially when considering the role that cosmic rays play in the formation of elements and the energy balance of galaxies. Cosmologists have long theorized that the distribution of galaxies in the universe is not random but rather forms a vast network of structures, often referred to as the cosmic web. This web consists of filaments of galaxies, separated by enormous voids, which together create the large-scale structure of the universe. Interestingly, magnetic fields may play an important role in the formation and evolution of this cosmic web. Magnetic fields could affect the dynamics of the gas that fills the cosmic voids, possibly acting as a kind of cosmic glue that helps to bind the filaments of galaxies together. The interaction between the intergalactic medium and these extragalactic magnetic fields could help us understand how the cosmic web was formed and how it continues to evolve over time. While extragalactic magnetic fields are already known to be widespread, their exact origin remains a subject of great debate. One possibility is that these fields are primordial, meaning they have been present since the earliest moments of the universe. If this is the case, they could provide valuable insights into the conditions that existed during the formation of the universe and the early stages of galaxy formation. On the other hand, some researchers believe that these magnetic fields are the result of processes that took place much later in cosmic history, potentially linked to the evolution of galaxies and clusters over billions of years. Either way, the origins of these fields are closely tied to the broader story of cosmic evolution, and understanding them could provide essential clues about the formation of the universe itself. There is also the tantalizing possibility that extragalactic magnetic fields might be connected to some of the most mysterious aspects of the cosmos, such as dark matter and dark energy. These elusive substances are thought to make up the majority of the universe's mass and energy, yet they remain largely invisible and undetectable. What if magnetic fields could provide a bridge, connecting the known universe with the invisible realms of dark matter and dark energy? Some scientists speculate that these fields might offer a way to probe the nature of these substances, potentially unlocking the secrets of the universe's most fundamental components. Magnetic fields may not only provide insights into the large-scale structure of the universe, but also into its hidden, mysterious components. With advancements in technology and observational tools, astronomers are beginning to map the magnetic fields that stretch across the universe. Instruments like the upcoming James Webb Space Telescope and ground-based observatories are expected to provide unprecedented insights into the behavior of these fields on a variety of scales. By studying the polarization of light from distant galaxies, astronomers can begin to piece together the structure of the magnetic fields that stretch between these galaxies, helping us understand the interactions that shape the universe on its largest scales. The next decade of astronomical research promises to be an exciting one for the study of extragalactic magnetic fields. As technology continues to improve, we will be able to observe these fields in greater detail, potentially unlocking new mysteries about the forces that govern the universe. With the potential to revolutionize our understanding of everything from galaxy formation to the nature of dark matter, the study of extragalactic magnetic fields is poised to become one of the most important areas of research in modern astrophysics. Moreover, it's worth considering the implications of these magnetic fields on a cosmological scale. For example, could the alignment and behavior of these fields provide clues about the expansion of the universe or the cosmic inflationary period following the Big Bang? Could they help us understand the way that galaxies cluster together, or how supermassive black holes develop and grow over time? These are just a few of the many questions that researchers are actively working on, and as new data is gathered, we can expect even more profound insights into the role that extragalactic magnetic fields play in the universe's grand design. It's also crucial to understand the broader implications of this research. The exploration of extragalactic magnetic fields and their interactions with cosmic structures has the potential to unlock new ways of thinking about the universe. It could lead to entirely new theories about the nature of gravity, the behavior of fundamental particles, or even the laws that govern the cosmos. In many ways, we are on the verge of a new frontier in cosmology, one that could completely reshape our understanding of how the universe works. The study of extragalactic magnetic fields and bridges is not only a fascinating scientific endeavor but also a key to unlocking some of the most profound mysteries of the universe. From their role in shaping the cosmic web and influencing the formation of galaxies to their potential connection to dark matter and dark energy, these magnetic fields offer a new lens through which to explore the cosmos. As we continue to study them, we are bound to uncover more surprises and deepen our understanding of the forces that govern the universe. The cosmic web, with its vast networks of galaxies and magnetic structures, is a reminder that the universe is far more interconnected and dynamic than we ever imagined, and we are only just beginning to grasp its complexity. As we continue to investigate the mystery of extragalactic magnetic bridges, we begin to realize that these phenomena are not just awe-inspiring cosmic curiosities but also critical pieces of the puzzle when it comes to understanding the large-scale structure of the universe. The vast distances between galaxies and galaxy clusters make it difficult to imagine how these structures could interact, but when we factor in the influence of magnetic fields, the picture becomes clearer. The more we explore, the more we come to appreciate how magnetic fields can serve as a cosmic connective tissue, linking distant regions of space together, and playing an essential role in shaping the behavior of matter across the universe. It's important to remember that extragalactic magnetic fields are not limited to isolated regions of space. Rather, they represent a more widespread and intricate network, forming vast magnetic loops that stretch between galaxies, clusters, and even the largest cosmic structures. These fields often manifest as large-scale coherent structures, forming bridges that can span millions of light-years in length. These magnetic bridges may seem abstract at first, but they play an undeniable role in the dynamics of the cosmic environment. By interacting with the ionized gas that permeates galaxy clusters, magnetic fields can help drive the behavior of galaxy formation and evolution, particularly when it comes to the interaction between hot gas, supermassive black holes, and the dark matter that pervades the universe. When we look at galaxy clusters, for instance, we see that they are often surrounded by a hot, diffuse gas that can be incredibly difficult to study. However, through the influence of magnetic fields, this gas can be traced and studied in ways that were previously impossible. By understanding the magnetic fields that permeate these clusters, we can gain insight into the processes that govern galaxy formation, growth, and destruction, as well as the role that dark matter might play in shaping these processes. The magnetic fields could provide a mechanism for transferring energy between different parts of the cluster, which could help explain the observed behavior of galaxies within these clusters. It is through the study of these magnetic bridges that we might begin to piece together the mechanisms behind galaxy evolution and the formation of large-scale cosmic structures. One particular area where extragalactic magnetic fields are of significant interest is in the study of active galactic nuclei, AGN. AGN are the energetic centers of certain galaxies, powered by supermassive black holes that are actively consuming matter. As material falls into these black holes, it can generate vast amounts of energy, much of which is released in the form of relativistic jets. These jets can extend far beyond the host galaxy, stretching across millions of light-years and, in some cases, even forming powerful magnetic bridges that connect multiple galaxies in a cluster. The magnetic fields involved in this process are thought to play an essential role in the formation and acceleration of these jets. They may not only help to guide the jets along specific paths but also regulate their energy output, preventing the jets from dissipating too quickly and allowing them to travel vast distances without losing their strength. The relationship between magnetic fields and these powerful jets raises interesting questions about the nature of cosmic energy and the flow of matter across the universe. Could magnetic fields serve as a kind of energy conduit, facilitating the transfer of energy from one galaxy to another? Could they provide a mechanism for redistributing energy across the cosmos, helping to balance the energy budgets of galaxy clusters and the intergalactic medium? These are the kinds of questions that continue to drive scientific inquiry in this field, as researchers seek to understand the profound effects that magnetic fields have on the structure and dynamics of the universe. Moreover, extragalactic magnetic fields are crucial when it comes to understanding cosmic acceleration. We've already discussed how magnetic fields influence the behavior of cosmic rays, but there is another facet to consider: the role of magnetic fields in the acceleration of particles to relativistic speeds. Cosmic rays are thought to be accelerated by a combination of processes, including shock waves, turbulence, and magnetic fields. However, it's possible that extragalactic magnetic fields play a role in this process as well. By acting as a mechanism for energy transfer, magnetic fields could help to accelerate particles over vast distances, causing them to gain energy as they move through different regions of space. This acceleration could be critical for understanding high-energy astrophysical phenomena such as gamma-ray bursts, active galactic nuclei, and the formation of cosmic jets. Another avenue of research involves the role of magnetic fields in galaxy mergers. When galaxies collide or pass through each other, The resulting interactions can lead to significant changes in their structure, dynamics, and magnetic fields. The interaction between the magnetic fields of the colliding galaxies can give rise to complex phenomena, such as the formation of new magnetic structures, the reorientation of existing fields, or the creation of new cosmic bridges. These events can help researchers to understand the complex behavior of magnetic fields during galaxy mergers and the impact that such interactions have on the evolution of galaxies and clusters. The interplay between magnetic fields and the intergalactic medium is another exciting area of research. The intergalactic medium, IGM, consists of the diffuse gas that exists between galaxies, and it is thought to contain a significant amount of the universe's baryonic matter. By studying the magnetic fields that permeate the IGM, astronomers can gain insight into the processes that govern the behavior of matter on the largest scales. For example, the presence of magnetic fields could help to explain the observed distribution of matter in the IGM and the way in which galaxies and clusters form and evolve over time. The IGM also serves as a key element in the process of cosmic reionization, which marks the transition from the opaque universe of the early cosmos to the transparent universe we observe today. Magnetic fields could have played a significant role in this process, influencing the behavior of gas and radiation in ways that we are only beginning to understand. There is also the possibility that extragalactic magnetic fields could help explain the origins of the large-scale structure of the universe. As we've seen with the cosmic web, galaxies are arranged in vast filaments that are connected by dark matter and gas. The magnetic fields that permeate these structures could provide the mechanisms for their formation and evolution, helping to guide the movement of matter and energy within these filaments. The study of these fields might help us understand how the cosmic web developed over billions of years and how it continues to evolve today. Finally, it's worth considering the broader implications of this research. As we continue to uncover the mysteries of extragalactic magnetic bridges, we may discover new ways to probe the unseen aspects of the universe, such as dark matter, dark energy, and the forces that govern cosmic acceleration. Magnetic fields may serve as a bridge between the visible universe and the mysterious realms beyond, providing us with the tools to investigate the most fundamental questions about the nature of reality itself. By studying these magnetic structures, we may not only gain a deeper understanding of the universe's large-scale structure but also unlock the secrets of the invisible forces that govern its behavior. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.